Module 1, why use concurrency? Topic 1.1, parallel execution. So Go language, a big property of Go language is that concurrency is built into the language. Now we're going to talk about this term concurrency. Right now I'm talking about parallel execution. Concurrency and parallelism are two closely related ideas, and we will be talking about the difference between them. I'm starting with parallel. But it's an important feature, and it's built into the language. Now this is as compared to other languages like C, and things like anything, Python, whatever. These languages, you can do concurrent programming in these languages, but it's not built into the language. Meaning usually what you do is you import some library, some external library, and then you can use the functions, and it interacts with the operating system and so on. GoLang, though, they decided, look, concurrency is important enough, we're going to actually bake it right in so the constructs are part of the language. And so that's a good thing. It makes it actually, usually the constructs are easier to use. So we're going to talk about that. Now, right now I'm just describing parallel execution because I really want to motivate why you need concurrency. Okay, why do you need concurrency? Now, parallel is not the same as concurrent. We'll get to it, but they are similar. So parallel execution is when two programs execute at the same time. Okay, exactly the same time. So then you can say these two programs are executing in parallel. So at some particular time, any particular instant in time, you could say there's an instruction from one executing and an instruction from the other executing at the same moment, then they are executing in parallel. Now generally, processors, certainly processor cores, are made to execute one instruction at a time. Now there are different architectures that do things differently, okay? There are a wide range of architectures, and this is an architecture class. But generally, one core runs one thing at a time, one instruction at a time. So if you want to have actual parallel execution, two things running at the same time, you need two processors, or at least two processor cores. You need replicated hardware. You would need to have one CPU and another CPU. So for instance, if you had two completely separate computers, they can clearly run two different programs at the same time. Or they can be the same computer, but maybe it's a multi-core processor. It's got 4 cores. Then you could run 4 different instructions at the same time, one on each core. But understand that in order to get actual parallel execution, you need multiple versions of the hardware. You need replicated hardware in order to get parallel execution. Now, this is not the same as concurrency. This is not the same as concurrency, but we'll get to the difference in a second. So why should you do parallel execution? What's good about it? The best thing about it is that tasks can complete more quickly. Now, by this I mean a particular task doesn't complete more quickly just because you're running it in parallel with another task. But you get better throughput, meaning overall all the tasks are completed more quickly if you're doing 2 things instead of 1 at a time, right? Or multiple, right? So parallel execution can speed things up, give you a better throughput overall. And my simple example is, say you got 2 piles of dishes to wash, okay? So when you wash a dish, you gotta wash it and then dry it, right? So if you have 2 dishwashers, they can cooperate and work faster, right? And now how they cooperate is going to depend on the hardware that they have available to them, right? So some tasks have to be performed sequentially though. So for instance, so when you're drying and you're washing a dish, you clearly have to wash the dish before you dry the dish. Right? That's sequential. They have to go in that order. They cannot happen at the same time, right? So parallel execution is not this catch-all that makes everything faster. Certain things can't be executed in parallel. They have to be executed sequentially, one at a time, okay? So you got to wash the dish before you can dry the dish. But you can have a system, say I had one sink, okay? One sink and one drying rack. So that's my hardware available to me, and one dish rag, for washing, one for drying. So I can have these 2 people work where one person washes a dish and he hands it to the other person who dries the dish, right? So then in that way, somebody can be washing at the same time somebody's drying. Just keeps passing it over. So then you're essentially getting some kind of parallel execution. Staggered parallel execution, but both people are working at the same time, okay? So then you get speed up. You get a good throughput. Right, but even though these tasks have to happen sequentially, you can still get a speed up. But I guess a key thing here is that some tasks are more parallelizable than others. Okay, so like for this dishwashing task, you can't just say, okay, you two guys both wash this dish at the same time and you both dry it. If I only have one sink, only one person can, say, get into the sink, so one person can wash at a time. And I only have one drying rack, so one person can dry at a time. So because I don't have the hardware, I can't parallelize them, right? I would need two sinks to parallelize that to do washing at the same time, and two drying racks to do drying at the same time. But in addition, I can never parallelize the washing of a dish with the drying of the same dish, right? You got to finish the washing before you start the drying. So some parallelization, even if you have extra hardware, I could have 100 wash and sinks in there. I still can't do washing and drying of the same dish at the same time. So some tasks cannot be parallelized even with the excess hardware. And that's important to know because people often think, well, I can just take anything and speed it up through parallelization. That is not true. Some things cannot be parallelized, and that's that. You know, it's just the nature of the computation. Certain things have to be done in a certain order, can't be done at the same time. Module 1, Why Use Concurrency? Topic 1.2, von Neumann bottleneck. So we're talking about doing things in parallel, using concurrent programming to execute code in parallel. But why do that? Okay, coding in parallel, writing concurrent code is hard. Okay, I haven't brought that up yet, but as we get into it, we'll see it is hard for a bunch of reasons. And actually, if you look at most undergraduate curriculum, students don't learn that. You learn sequential programming, right? In C or Python or Java or whatever language, you learn sequential programming. And now, maybe sometimes an undergrad will have a class on parallel programming, but maybe it's optional, maybe they take it, maybe they don't. But the vast majority of programming classes that you see at the undergrad level anyway, they are not talking about concurrent programming. They're just talking about sequential, regular old code, runs one instruction at a time. So programming concurrently is actually very hard. So why do it? Can we get a speed up without doing it? Right? Clearly, if you do things in parallel, you could get speed up. But do we need it? I would argue, and most people would argue, yes, we do right now. Okay. In the past, maybe we didn't need it. Okay, but now we really need it. So one way to do it one way to get speed up without parallelism is to just speed up the processor. Okay, so just make a new processor that runs faster than the old processor, and then you get speed ups, and you don't have to change the way you write your code. Now, this had been the way of things until, I don't know, till recently. When I say recently, 5, 6, 7 years ago, something like that. Until sort of recent years, that had been the way of things. So the way things sped up, majority of the way code sped up was because the processors were being built faster. Now, I'm from the hardware design community, and I've always felt that these programmers got away with murder because their speed ups were all on our back, right? We design better, faster processors. They didn't have to do anything, and they just get better, faster running code, okay? But that has really stopped now, okay? So part of the problem, there are several reasons why that stopped, okay? It used to be when I was a kid, and I'm old, okay? But when I was an undergrad, okay, 86 to 90, I was an undergrad. Back then, I remember a machine would come out, and you'd buy it and you think, oh, this is the fastest thing out there. And seriously, a few months later, maybe half a year later, they'd have, for the same price, something that was significantly faster. And it would just kill you, right? You're like, wow, I just bought this machine, and now they got something faster. The clock rate and when I say faster, I mean the clock rate went up, okay? So the clock rate would be 20% higher than the thing I just bought. And that was very frustrating. But this used to happen all the time. Like every short period of time, clock rates would get faster and faster. And as the clock rates get faster, the code executes faster generally, modulo memory bottlenecks, which we'll talk about now. But processes would get faster and faster. Now, another limitation on the speed that you have now, even now, is this what you call the von Neumann bottleneck. Okay, so it's the delayed access memory. So if you think about the way a processor executes code, there's a CPU that's executing the instructions, and there's memory. And the CPU has to go to memory to get the instructions, also to get data that you want to use. You want to say x plus y equals z, you got to go to memory, grab the data out, add them together, put the result into z, or rather into x. But you have to access memory. So the CPU is regularly reading from memory, writing back to memory. And memories are always slower than the CPU. So even if you crank up the clock speed, make that thing work at a lot faster, the memory is still slow. Now, memories speed up slowly over time, but a lot slower than the clock rates would speed up. So you get what's referred to as a von Neumann bottleneck, where even if you crank up your clock speed, you could double your clock speed, but your code only runs a little bit faster. And that would be because even if you crank up the clock speed, you're still waiting on memory, right? So you'd waste a lot of time just waiting for memory access. So what people do for that, or have done in the past for that, and they can do less so now. What they have done for the past for that is they build cache, so fast memory on the chip. So you don't have to go to main memory, which is too slow. You go to fast cache. So they like to pack more and more cache onto the chip, and it speeds things up. So that's what traditionally had been done until, when I say recently, I don't know, 5, 6, 7 years, something like that. That's what happened. And so clock rates would go up, memory cache capacity would go up, and so speed would go up. These performances on these processes would just go up and up and up. And as a programmer, you don't really have to do anything. You could just write your code the same old way you wrote your code and expect that it would speed up magically because the processes themselves were getting improved. So that's how it used to be. That's not how it is now. It's changed for a couple of reasons. First thing is that Moore's Law, which I'm about to describe, has really died. I don't know what the right term is. It doesn't really happen anymore. Okay, so Moore's Law, it basically predicted that transistor density would double every 2 years. 18 months, no, 2 years was the number. Transistor density would double every 2 years. Now, these processes, they're all a pack of transistors. Lots of transistors that are used to do computation. So if you can double the transistor density, then basically the transistors are getting smaller and smaller, and they switch faster when they're smaller, meaning they can go high to low faster. So as they get smaller, they get faster, and so as the density increases, you get this speed up, this natural speed up in the transistors. Now, this Moore's Law, it's not really a law. Law is sort of a bad term. It is not a physical law. It's just an observation. So what was observed was that if you draw, actually you can see this I don't have a picture of this image, but you can see processor speeds, clock rates over time. Right? So you have time going up, clock rates going up, and they were going up very fast, right? Now they've tapered off now. If you look recently, you can see that it's tapered off, and the clock rates just can't get any higher, can't get much higher than they are. But what we were getting for a while was this exponential increase in density over time. So you get an exponential or roughly exponential increase in speed. So Moore's Law was sort of doing everything for us, right? Or most of the things for us. It was just giving us a speed up. Programmers didn't have to worry about things. And now, of course, in order to make Moore's Law happen, hardware designers had to work our butts off in order to achieve this. I mean, it's not sort of magic that transistors just get smaller, would just get smaller every few years. That was hard work on the part of hardware designers, okay? Figuring out how to get these transistors smaller and still accurately made and all this. Very hard work, but they were consistently doing it, okay? So software people had an easy time of it. But that's not how it is anymore. That type of thing has gone away. So software, in order to continue getting speedups, has to do something else to keep achieving those speedups over time. Module 1, why use concurrency? Topic 1.3, power wall. So as I was saying, this speed up that you get from Moore's Law, so density increase, which leads to a speed up and performance improvement, it can't continue. So you might say, well, why? Why can't that just go on forever? Reason why is because these transistors consume power. And so, sure, the density of transistors can go up and up and up on these processors, but these transistors consume a chunk of power. And the power is becoming a critical issue. And they call it a power wall, okay? So as you increase the number of transistors on the chip, increasing the density, that would naturally lead to increased power consumption on the chip. Now, back in the old days, power consumption was really low, and people didn't use battery power so much. So nowadays, though, everything's portable, running off of a battery. Also, the density has gotten so darn high, the power use has gotten high. Now, power use, even if you are plugged into the wall and you have access to power, high power leads to high temperature, right? If something is consuming a lot of power, it's going to be physically hot. So I don't know if you've ever opened up a desktop computer. You look inside, if you look at the motherboard, there's at least like a bunch of cooling fins. Actually, you can see this picture. There's a fan, right? Actually, this is a very common thing. Inside the board, there's a processor, the main processor. Say I'm using an i7, okay? So on the board, there's going to be an i7, but it will be, on top of it, will be a fan just screwed on top of the thing. A fan with a bunch of cooling fins, aluminum fins, just to release the heat, to let the heat dissipate, and then a fan just to air cool it, to blow the heat away. So this is necessary because these chips are running at such high power that they're heating up, and you need the cooling, right? And if you don't have the cooling, if you don't have this heat sink to dissipate the heat and the fan to blow away the heat, then it'll hurt the chip. Eventually, the chip just melts, physically melts. So this is basically what you're calling the power wall. So even if you could put more transistors on there, you got to be careful about power. Now, and specifically power and its impact on temperature. Okay, temperature is probably the biggest wall there, but power is also an important thing because if you want to have portable devices, you have battery, you don't want to run out of your battery instantly, right? So power all by itself is important, but the temperature is probably the biggest limitation because you will melt a chip if you don't cool the thing. And just to note, air cooling is the standard, right? I mean, anybody who's desktop, laptop, you air cool it, or server too, you air cool it. Now you could go to an extreme where you say, look, I'm going to water cool it. Okay, and actually supercomputers do this. They have pipes, they're plugged into a liquid cooling system, and they typically don't use water. They probably use liquid nitrogen, some super cool fluid. They pump that through the device to cool it much better. It gives you much better cooling. But nobody wants that on a either laptop or desktop to have to plug it into a water system, right? Maybe as a supercomputer that's okay, but air cooling is the best we're going to do. In practice, people want air cooling. They don't want to have to go to liquid cooling, right? So you're at this limit where you can only dissipate so much heat. So to be a little bit more specific about these limitations that happen due to power use, what I'm showing up here is this generic equation for power. Okay, P power. And there are a bunch of, there's an alpha. So alpha is a percent of time switching. So what that means is that these transistors, they consume power, or what's called dynamic power. They consume power when they switch. So when they go from 0 to 1 or 1 to 0, they consume power. If they're just holding constant, if they're not switching at all, then they don't consume dynamic power. So that alpha is a number from 0 to 1, which indicates how often they're switching. Now, note that if you design your system well, they're switching a heck of a lot, right? You probably want to use the transistor to do computation, so that alpha should be fairly high. C is a capacitance. We don't want to go into detail what that is, but it's related to the size of the transistor. So capacitance goes down as the transistor shrinks, which is a good thing. So power will go down to some extent. F is the clock frequency. That is what you want to increase, right? To make your device work faster, you want to increase the frequency. But note that if you increase the frequency, you're increasing the power. Now then, there's V squared. That V is the voltage swing from low to high. So what that means is that basically, whenever a transistor goes from 0 to 1, 1 to 0, those binary values, those are actually analog voltages. So 0 is typically 0 volts, and a 1 might be 5 volts. Like if it's an Arduino or something like that, it goes from 0 to 5 volts. Now, in a real processor, they're going to reduce that. So that V is important because notice that V is a squared factor, right? So if you reduce the voltage, you can significantly reduce the power. So maybe you're going to use voltage swing from 0 to 1.3 volts, or 0 to 1.1 volts, something like that. So it's so voltage is sort of the first thing that you want to reduce if you want to save power. So Dennard scaling is another thing. It's it's paired together with Moore's law. Dennard scaling is what gave us these speed ups that we get over time. The idea with Dennard scaling is that the voltage swing should scale with the transistor size. So as the transistors get smaller and you get more density, more transistors on a chip, you would also like to scale down the voltage at the same time. Because basically for the power reason I just told you, that equation, voltage has a big impact. So if you can scale down the voltage, then you can keep power consumption and then temperature low or within limits. So that's what you want to do. You would like to have Dennard scaling. The problem is Dennard scaling can't continue forever. Voltage can't go too low for physical reasons. First reason is that the voltage swing between low and high has to be higher than the threshold voltage of the transistor. So transistors have what's called a threshold voltage. Below a certain voltage, they can't switch on. So you got to have at least enough voltage to hit the threshold. Now, as you shrink it, you can manipulate the threshold voltage, but it can only go physically so low. And then another thing is that noise problems occur. So One good thing about having a big voltage swing from 0 to 5 volts is if there's some kind of noise on your signal, right, in your system, which alters your voltage. Say your voltage goes plus or minus 0.5 volts. So instead of 5 volts, you get 4.5 volts. That's okay because well, it's only minus 0.5 volts. So even though the voltage is 4.5, it had to have been 5. That's a high, right? And if instead of 0 volts, you get 0.5 volts, you say, look, it's not exactly 0, but it's close. Right, so you can tell the difference. But the reason why that's okay is because the voltage swing from 0 to 5 volts is pretty big. If you have your voltage swing come down to, say, 1 volt, say you use 0 volt as a low and 1 volt as a high, then if you have the same noise in there, 0.5 volts of noise, then when the voltage is 0.5 volts, you can't tell if it was high or if it was low. So you can't recover from the errors. So you become less noise tolerant. And that's a big problem because there's always noise in any kind of practical system. So for these reasons, Dennard scaling can't continue. You can't keep scaling the voltage down. There's a limit to that. In addition, none of this considers leakage power. So the equation I showed for power is what's called dynamic power, the power that the transistor uses when it switches, when it goes from low to high, high to low. There's also another kind of power called leakage power, which the transistor leaks off power even when it's not switching. Now, in the old days, leakage power was pretty low compared to dynamic power, because mostly because everything was big. So leakage happens when you have sort of thin insulators, right? So if you think about basically how leakage happens is there's a conductor, and current leaks from one to the other. There's an insulator in between, but the insulator is not thick enough. Now, in the old days, everything was big. When I say big, I mean, scaling was different. It's not big, it's still microscopic, but relatively big. So you have thick insulators. So it's hard for leakage to happen. But as you scale everything down, these insulators become thinner and thinner, and leakage can occur. And so leakage power has been growing over time. So leakage power, even scaling the voltage, doesn't save you with the leakage power. Leakage power is actually increased over time. So for these reasons, the power, you can't continue the Dennard scaling. You can't keep scaling the voltage down, so that power equation keeps going up. And that's what they mean by power wall. Basically, we're at a place where if you get this thing running any faster, the temperature is going to go so high that things are going to actually melt. The device will actually melt in the system. So what happens is, there's our power equation again. You can't increase the frequency, not without melting things. So what do you do? So what do designers do in order to improve performance, even though they can't increase the frequency? And but beyond just improving performance, say you're Intel, you want to sell chips, right? So if say you come out with a generation chip that's running at 4 gigahertz, and the next generation is also at 4 gigahertz, people may not buy the chip. Right? They need some reason to buy this thing. It's got to be some improvement. So what do people do? They increase the number of cores on the chips. This is where you get multi-core systems. So you probably heard of this. A processor core, it basically executes a program, roughly, and you can have multiple of them. So, an i7 might have 4 processor cores or something like this. They have variable numbers of cores. But they're still increasing density. They're just having more of this replicating hardware on the chip. But they don't increase the frequency. They don't increase the clock frequency. They keep it roughly the same. So, for instance, clock frequencies, they go up slowly, but much more slowly than they used to go up. But the number of cores still continues to increase. Now, the thing about having a multi-core system, having lots of cores, is that you have to have parallel /concurrent execution to exploit multi-core systems. Meaning, if you got 4 cores in your processor, and you can't run anything in parallel, right? Then what's the point of having 4 cores? Then you're using 1 core and the other 3 cores are sitting idle. So in order to exploit these multi-core systems and or get speed up, you have to be able to take your program, divide it amongst a bunch of cores, and execute different code concurrently on the different cores. Okay? So this is where parallel execution becomes necessary. In order to keep achieving speed up in the presence of multi-core systems, you got to be able to exploit this parallel hardware. So you need to be able to write concurrent code just to exploit it. So that is really the motivation. This is why concurrency is so important nowadays, because the programmer has to tell the program how it's going to be divided amongst cores. Right? That's really what concurrent programming is doing. It's saying, look, here's a big piece of code. You can put this on one core, this on another core, this on another core. Right? These things can all run together. That's what the program is doing when you're doing concurrent coding. And you have to do that. Meaning actually, it's funny, there are things called parallel compilers. Okay, there's a big research field, or there was anyway, there still is, in parallel compilers. And what they're supposed to do is they take sequential code, a regular C program or whatever language, and they parallelize it. So they do concurrent programming automatically for you. They say, look, here's a big piece of code. I'm going to chop it up into these different tasks that can all run concurrently. That is an extremely hard problem. And it basically, I hate to say it, but it doesn't work that well. Now, I know when I say that, I'm going to offend a bunch of researchers, but it doesn't work that well. And so what has to happen is, since you can't automate that easily, you need the programmer to actually do that. That's what concurrent programming is. The programmer is saying, look, I can decompose this task in the following way. It's hard, but it's important now, because if the code programmer doesn't do it, then it's not going to get done. Everything runs on one core, and then what's the point of having 4 cores if you're running everything on one core? Thank you. Thanks. Module 1, why use concurrency? Topic 2.1, concurrent versus parallel. So I've been talking about parallel execution. Now I'm going to use this term concurrent. Parallel and concurrent are related ideas, but concurrent programming is really what we're going to do, and they're slightly different, this parallel versus concurrent. Concurrent execution is not necessarily executing at the same time. It could be, but it's not necessarily. So concurrent, you can call 2 tasks concurrent, and by task, I mean, let's think of a program for a second. We'll get more specific about what a task is later. But you say 2 tasks are concurrent if the start time and the end time of the tasks overlap. Okay, so that range of time between start and end for these 2 tasks, if they overlap, then you say that it is concurrent. That does not mean that they're literally executing at the same time. Where with parallel, they have to literally be executing at the same time. So if you look at the picture, on the left you got task 1, task 2, this timeline. Time's increasing down. Okay, so there's a start. If you look at task 1, it starts early. Then it executes. Where you see that black line, that black vertical line under task 1, it's executing. Okay. And then there's that blue dash line where task 1 stops executing, task 2 starts executing. Then task 2 executes, it starts, it ends. And then when it's done, task 1 continues to execute until its end. So notice it says start 1 and end 1 for task 1, and start 2, end 2 for task 2. Now these regions of time between the start and the end of task 1, start and the end of task 2 on the left, they overlap in time. Okay, so task 2's start and end time overlaps with task 1's start and end time. So you would say these 2 are executing concurrently. Now they are not executing in parallel, because if you look at any one time instance, either task 1 is executing or task 2 is executing. So they are not parallel, but they are concurrent. Now on the right-hand side, we're showing actual concurrency. Actual parallelism. So you got the 2 tasks, and again, they have the different start and end times that overlap, so they're definitely concurrent. But also, you can see in that middle region of time, when task 2 is executing, task 1 is actually executing at the same time. So on the right, we're seeing actual parallel execution. While on the left, we're seeing concurrent execution. So their times overlap, but they're not actually executing at the same time. Now, one thing to note is that on the left, the concurrent execution, the completion time for both tasks is longer than on the right, the completion time when they're working in parallel. So parallelism gives you that. It gives you a better and improved completion time, right? We already talked about that. So one might ask, why do concurrent execution if you're not executing at the same time, if it's not actually parallel? Maybe concurrent execution isn't that beneficial, right? I mean, why not just do task 1 and then do task 2 right after it, forget the concurrent execution, and the end time would still be the same? Well, there is a benefit, and we'll talk about that. Okay, so just again to reinforce this difference between concurrent and parallel tasks need to be executed. Parallel tasks must be executed on different hardware, right? In order to execute in parallel, you need different hardware, different cores typically. Concurrent tasks may be executed on the same hardware, but may not. Right? You could have them on the one processor core, and since they're actually alternating, right, like we saw in the last slide, you can execute them on one piece of hardware, one core, and you can still say this is concurrent execution. But only one task is executed at a time. So this process of mapping the tasks to hardware is not directly controlled by the programmer. So when I say mapping the tasks to the hardware, you've got these tasks, task 1, task 2, that you need to perform on some hardware, core 1, core 2. And determining which core is performing which task, that's what I'm calling hardware mapping. That is not directly controlled by the programmer. Okay, and certainly not in Go. Now, there exist languages where the programmer directly controls that sort of thing. Those are generally considered, I'll call them exotic. They're not commonly used, put it like that. But that's a complicated thing, and it's not part of Go. And it's not part of most languages either. So most of the time, in a language like Go, when you do concurrent programming, the programmer, in doing their concurrent programming, they're determining which tasks can be executed in parallel. Also, they're determining a few other things like what kind of communication there is between the tasks. Maybe one sends data to the other. Also, synchronization events. We'll get into all these details later. But maybe, so for instance, maybe this test has to do some stuff before this test does its other stuff. So they have to synchronize on a certain time. This must be finished before this time. This can finish after the time, something like that. We'll talk about that, okay? But that's what the programmer does. The programmer describes what can be executed in parallel, not what will be executed in parallel. So what will be executed in parallel depends on how the tasks are mapped to hardware. Now, how the tasks are mapped to hardware, that is not directly in the control of the programmer. That's left to the operating system. Also, the Go runtime scheduler. That does part of the task too. We'll talk about that too. That's part of the Go language, actually. It gets compiled into your code, and it handles some of that too. But concurrent programming is where the programmer defines the possible concurrency, what can be done in parallel, what can't be. But what actually is done in parallel and what is not depends on the mapping to hardware, and that's not under the control of the programmer. Now, let's say you're doing this. Say you have one core. Okay, you're doing concurrent programming, but you've only got one core, so you can't actually get parallelism. So one might say, look, why bother? Right? Why go to all that effort of concurrent programming if I'm only going to get concurrency anyway? Everything's happening one instruction at a time. These tasks can't actually run together at the same time. So even though you can't get parallelism, maybe you can't get parallelism because you don't have concurrent, you have multiple processors, multiple cores, you can still get significant performance improvement just from using concurrency. So the reason why this happens is because typically tasks have to periodically wait for some event, some slow event. Now, there's many of these slow events, typical input-output things. So the idea is that in a machine, there's a CPU, a processor, and that runs fast. But when the processor has to communicate with other things that are not that are other chips, on the same board, that is slow. So for instance, say I got my processor and it needs to talk to some memory card. That is far away on the board. When I say far away, I mean this far, but that's far. In terms of signal transmission, that's far. So it's got to communicate with a memory to grab some data from memory. And memories are slow, right? So you typically have to wait for that. Maybe it wants to send data on the network. So it's got to communicate with this Ethernet card or Wi-Fi card, right? And the Wi-Fi card is slow. It takes a certain amount of time to handle the communication, to receive or send. So anytime the CPU wants to do, or maybe you want to put something on the screen, right? You got to go to a video card. So the CPU is communicating with a video card, and that has a certain delay. So when you have these I/O activities where the CPU is communicating with something else on the board but separate from it, those are slow. And often the code has to wait until those things are done. So for instance here, got this really simple instruction, x equals y plus z. So in order to do this instruction, you've got to read y and z from memory, and then you can compute the addition, and then you can put the result back in memory, in x, right? These memory accesses, reading y and z from memory, can take over 100 clock cycles just waiting on memory to grab the data from memory. So you can, the add instruction itself takes you 1 clock cycle, but you might be waiting 100 clock cycles just to read the data from memory. So when these type of delays, these pauses happen, they don't happen often, hopefully. It depends on how your code's written. Hopefully they don't happen too often, but they can, depending on how you access memory access patterns, that sort of thing. When they happen, you would rather not have your processor just waiting there for 100 clock cycles waiting for memory. It would be better if the task that's doing this x equals y plus z, that task, it has to wait for 100 cycles, but in the meantime, you would like to have that processor core executing some code, some useful code. So if you have multiple tasks that all can execute, when task 1 is waiting for memory, task 2 can execute. Right? And then when task 2, maybe it hits a memory access, then task 3 can execute while the other guys are waiting. Right? So that's called hiding latency. That's generally what you refer to as hiding latency. So there's a latency, like a wait time latency. So say I'm going to memory, I need to wait 100 cycles. You can hide that latency by just taking another task that's ready to run and execute that while you're waiting on the first event. Okay? So even without having parallel hardware, having multiple cores, say, just writing concurrent code can give you this significant advantage in performance because your program no longer has to wait on I/O, input-output accesses, whatever type of input-output accesses. No longer has to wait. It can just run in a program that's ready. And so things can still get done faster. So concurrent programming is useful even without parallel hardware. Now what I'm showing here is a picture of that hardware mapping. I was talking about this hardware mapping concept. In the top, I'm showing what parallel execution might look like. Bottom, I'm showing what concurrent execution might look like. So the idea here is, if say look at the parallel execution one first, you got task 1, task 2. So imagine these as blocks of code written in whatever language, Go or whatever it is. And at the bottom, you got core 1 and core 2. So these are 2 cores in a 2-core system. This hardware mapping is a task of saying this task runs on this core. So you can see with the parallel execution, I've got mapping these 2 tasks to run on 2 different cores, task 1 and core 1, task 2 and core 2, so they can execute in parallel at the same time. In the bottom, you do a different hardware mapping. You say, look, I got 2 tasks, and they are both executing on the same core. That would be concurrent execution. But key thing here is that this hardware mapping task, from the task to the core, that is not directly under the control of the programmer in Go or any other sort of standard language. So just to give you an example why that's not, you might actually argue, well, look, why not? Why not let the programmer do it? That is a hard problem. It is a difficult problem. And programmers generally don't want to do that. It would slow you down, okay, in writing your code. It makes your coding a lot harder if you actually perform the hardware mapping. And there's a lot of research in doing this hardware mapping and automatic techniques for doing it. It's a hard task. The reason why is because these hardware architectures can be complicated. And there are a lot of things that need to be considered when you're deciding which core is going to perform which task. And it would be a really big burden on the programmer to have to consider all these factors. And the programmer would have to be completely aware of the hardware, of the underlying hardware architecture. One good thing about traditional programming languages, like GoLang, but also Python, C, whatever, is that when you're writing code in these languages, you are not directly aware of the hardware of the underlying hardware architecture. You don't know, is this an i7 or is this an i3 or whatever. You don't know that, and you don't care. Okay, and you don't know exactly what the architecture looks like, and you don't generally care. Now, to some extent, you care a little. You might want to know, look, I have at least this much memory. Maybe you care sort of at a broad level. But the details of the hardware architecture, your coding is not dependent on that, and you really don't want it to be because it is complicated. So what I've drawn here is a picture of a relatively simple, arbitrary multi-core system. And this multi-core system has got these 4 cores, those blue cores around the edges. It's got 4 caches, local caches for each core, which is extremely common. Actually, this is a simplification of what you would expect to see. But each one's got its local cache. And then in the middle is a shared memory that all of them share and can read from and dump into their caches and so on. So when you're figuring out this hardware mapping, saying, look, this task should be performed on this core, this on this core, one big consideration is where is the data? So what I mean by that is if a particular core 1, let's say, so core 1 is going to perform this particular task, then it needs to access the data that the task uses. So where is the data located? The data, you want it to be in the local cache for that core. But say the data is in the shared memory or in the cache for another core or something like that. If the data is not where you want it, then if core 1, so for instance, core 1 is performing a task, but all of its data is on core 2's cache, then you've got to do these memory transfers. Right? And remember the von Neumann bottleneck, right? Memory is slow. So doing transfers from memory to memory, doing reads of memory can slow you down. So when you do this hardware mapping test, you got to think, okay, where is the data? Which memories have the data, which don't? And you basically want to put the task near the data. Also, what are the communication costs? So maybe maybe a cache to cache transfer is pretty fast because caches are fast, but if I could do cache to shared memory slower, right? So what you would have to consider which communications are fast versus slow. So it can get to be a very complicated problem. And I know that because I've seen plenty of research papers on that subject. It is a complicated problem. It is not something that generally a programmer wants to have to consider. So it is intentionally left out of traditional languages like Go. So in Go, we are doing concurrent programming. So we can define which tasks can be performed in parallel, but which tasks are performed in parallel is left up to operating system, Go runtime, something else. The programmer doesn't have to consider that. Thank you. Module 2, Concurrency Basics, Topic 1.1, Processes. So we're going to start talking about what a process is. A lot of concurrent execution, a lot of these ideas came from operating systems, okay? And the job of an operating system is really to give concurrency. We'll talk about this. To give to allow programs to run concurrently. So for instance, take the machine that I'm staring at right here that's running this PowerPoint presentation. It is running PowerPoint on it, right? But at the same time, it's doing other things in the background, and the operating system is allowing them all to be running concurrently at the same time, okay? So concurrency issues, a lot of concurrency starts with this idea of processes, and then we'll talk about threads and how they're related to processes, and then we'll get to Go and how it implements those things. So a process is basically an instance of a running program. There are things that every process has that's unique to it, a big hunk of memory. So if you got multiple processes running on a machine, every process has its own memory. It's a virtual address space, and we're not going to talk about virtual memory, but it has an address space, okay? It has addresses 0 to 2 gig. This process owns them, right? It has code, right? Every process is going to have its own code. It's going to have its own stack. Stack's a region of memory that handles function calls mostly. Heap, which is another region of memory where you do memory allocation, stuff like that. Shared libraries. Actually, shared libraries are shared. So sometimes those are, in fact, usually those are shared between processes. So shared libraries are actually not unique to a process. They're shared by definition. So they are shared by processes. But each process is going to have its own stack, its own code, its own virtual address space, a bunch of other things. Also, a process is going to have registers unique to it. Registers, in case you don't know, basically they just store values inside the machine. They're like tiny little super fast memories. They just store one value, one word, say. A program counter, right? Program counter, it's the register that tells you what instruction you're executing right now, or really the next instruction, what's the next one you're going to execute. Data registers, the stack pointer, that's another register that tells you where you are on the stack, stuff like that. So every process has this unique, it was typically called context, a bunch of memory, a bunch of register values that are unique to the process. And they're all needed to execute the program correctly. So every process is executing a running program. Now, an operating system does a lot of things, okay? But what essentially an operating system is something that allows multiple processes to execute concurrently, okay? And there's a lot of complexity behind that because they have to execute concurrently without bumping into each other, okay? So one process might say, look, I have addresses 0 to 2 gig. The next process thinks it has the same set of addresses. The next process thinks it has the same set of addresses. And so they have to be able to access addresses. Maybe they're all accessing address 1000, but they're not accessing the same address 1000. The operating system has to make sure, oh, this guy's 1000 is different than this guy's 1000, so that they don't interfere with each other. So another thing the operating system has to do is make sure that these processes get fair use of the processor, meaning this is concurrency, right? These processes are not actually executing in parallel, or that's our assumption right now anyway. So since they're concurrently executing, this process, like a process might get the CPU for a certain amount of time, and then the next process should get its turn. So processes are switched quickly, so like 20 milliseconds. That's a typical number. I think that's a standard number, a default number in Linux, where a process gets to use the processor, CPU core, for 20 milliseconds. Then the operating system says, okay, next guy's turn. Okay, and you can change that number, of course, but what happens is it's just moving them in and out so quickly that to a user's perspective, it looks like they're all running at the same time. So that's the main job of an operating system. And this task, just to give it a name, it's called scheduling. Deciding which process runs at which time, that's called the scheduling task, and operating systems do that. The user has the impression of parallelism even if it's not parallel. And although operating systems can employ parallelism, the operating system can map something to a different core, but generally, certainly right now, we're talking about single core operating system. And the operating system needs to give fair access to resources. So when I say resources, I mean things in the system other than the processor itself. So there's a processor itself. Maybe you give this guy 20 millisecond slice, that guy 20 millisecond slice. But also other things like memory. This one gets to use this region of memory. This one gets to use that region of memory. I/O devices. You get to use the screen now. Now you get your turn at using the screen, so on. So the operating system is basically managing a pile of processes and making sure they don't interfere with each other and they get fair use of the resources so they can all complete in a timely manner. Now, this is a picture of the task manager. So if you have a Windows machine, you hit Control-Alt-Delete, and you'll get a little prompt in the middle of the screen. It'll give you a bunch of options. You can select Task Manager. This is the Task Manager at the time when I made this slide. Okay. Now, Task Manager, what the Task Manager does is it shows you all the running processes. Now, and you can see there are many running processes. So, I can't even read it from here, but there are a lot of processes. And so, typically, like if I were to look at the Task Manager for the machine I'm looking at right now that's running the PowerPoint slides, it's got PowerPoint. That would be one of its processes that's running. But there would be sort of 30 other processes running, doing other background things. Maybe reading email, maybe serving a web server, maybe there's a web server on it, all kinds of background things, some security thing, checking for attacks. All that stuff would be going on at the same time. Now, when I say at the same time, it's all concurrent execution. And maybe there's only one foreground task, like this machine right here that I'm looking at. It's got PowerPoint running on it. That's the foreground task, right? That's the foreground process. But in the background, it's got a bunch of other things that get their turn and they do their thing at the same time. So you can always see the processes running just by looking at the task manager on a Windows machine anyway. Now, let's say you can see this on any machine, Mac OS, Linux, Mac OS, just for your information, it's basically a Linux. So you can look at that. If you wanted to see that, go to the command line, type PS. It lists all the processes running, or do a PS-L. You can see them all. And you would see similar information to this, although in a less easily readable format, you would see the same information. But this is the idea, that an operating system is allowing all these different processes to execute at the same time, or virtually at the same time, concurrently. Thank you. Module 2, Concurrency Basics. Topic 1.2, Scheduling. So, we're talking about how an operating system allows these processes to all execute concurrently, virtually at the same time, giving the illusion of parallel execution to a user. So what happens is the main task of an operating system is scheduling. So you might have many processes that are running. Like in this case, I have 3 processes that I want to run. Process 1, 2, and 3. And this little chart that I'm showing is execution over time. So time is increasing down. And these little vertical bars, they're colored, and each one's aligned with a process. And they're just showing how basically the operating system is making sure that one process gets a turn, so process 1 runs first. Then it gives process 2 a turn. Then it gives process 3 a turn. Then it goes back to 1 again, and so on. Now, these scheduling decisions, there are many different scheduling algorithms, ways of doing scheduling. And like, for instance, what we're showing here is basically what's called round robin. So you give each one a fair amount of time. Like in this case, I'm just going 1, 2, 3, 1, 2, 3, 1, 2, 3 over and over. Everybody gets the same slice over time. It's sort of a fair way to distribute. This is not necessarily how scheduling is done. Like, for instance, you get maybe you have a higher priority process. Some processes are more important than others, right? Some are, for instance, some processes, maybe they're interacting with the human, so they need to be prioritized better than something in the background, okay? So in that case, the scheduling algorithm built in the operating system might consider that and say, well, you're higher priority. I will let you have more time than I let this other task run, or something like that. Or I'll let you maybe process 1's higher priority, so it gets to be scheduled more frequently than process 2 or 3, something like that. There are many different scheduling algorithms, and you get a lot of this, especially with embedded systems, where you get certain tasks in an embedded system or an IoT device that are critical. Like if you take like a car, okay, let's take a car. Car's got many processors actually, and lots of things running. Say it's got a processor its processor is doing anti-lock braking, right? So you hit the brake, and the car's got the pedals, the brake pads have to come down on the wheel and brake it. Anti-lock braking, that would be considered a high priority process, okay? Now, on the other hand, maybe you got a stereo running. that is a low priority process. So what the processor should do, if they were both running on the same processor, which they typically are not, but if they were, then you would say that that anti-lock braking thing, that's got to have higher priority. So even if you're in the middle of playing some stereo music, that task would have to be stopped. So the operating system would say, okay, I'm putting you aside. Somebody just hit the brakes. We've got to go to the high priority task, the anti-lock braking. So there are many different scheduling algorithms for operating systems to handle prioritization and meeting deadlines and all this, and we won't go into it. But scheduling is the main task of an operating system. Now, when the operating system moves from one process to another, when it starts a process running and then it stops it and starts another process running, that act of switching is called a context switch. So what we're showing here, little graph where time's increasing down. You got process A is one column on the left, process B is another column on the right. Now, when you got the vertical line, like at the beginning, process A is running. Vertical line under process A. Then there's this blue area, this labeled context switch, and that's where it's switching from process A to process B. That's the operating system, changing from process A to process B. Then you can see process B runs, that vertical line under process B, and then there's another context switch from process B back to process A. Again, that's the operating system. So basically what's happening here is that when you're running a process, when you want to stop it, like running process A, you want to start running process B. What you have to do is take the current state of process A, and save it somewhere. So for later use, right? And then you have to bring in the state of process B, let process B run, and then later when process B is running, you want to go back to A, you take that state of process A that you saved, and you bring that back in so it can start from where it left off. Now, when I said the state, that's called the context, okay? And the state, it includes all those things that are unique to a process. So it's virtual memory system, like which parts of memory it can access, which it can't. All its register values, the program counter values, stack pointer, all that stuff. It's code, right? All that stuff is unique to a process. So we call that the state, sort of memory and registers associated uniquely with the process. When you do a context switch, you take that context, all that state information, you save it to memory somewhere for the process that you're throwing out. And then for process B, if you bring that one in, you find its state on memory and bring it all back in. Bring in its virtual address system and bring in its register values and all that so that process B can continue from where it left off. And then when you go back to process A, you do a swap again. Process B's state, its context is saved to memory somewhere. And then process A's state is brought in from memory back into the registers where it belongs. And process A can continue where it left off. So this context switch is performed by the operating system. So if we look at the chart that I show there, right? There's a time where process A is running, then there's a context switch, then process B, then the context switch, then process A. Those two context switch times, that's the operating system itself running, what's called the kernel. The kernel of the operating system, so the main code of the operating system. Let's think of it like that. And the context switch is the kernel of the operating system running. It's executing at that time. And typically what happens is you got a timer. So these processes all have timers. When the operating system starts process A running, it sets a timer, maybe a 10, maybe 20 millisecond timer. And when that timer goes off, process A is stopped and the operating system is executed. Then it does the context switch, and then it starts process B and it sets a timer again. So when the timer runs out again, then it does the operating system runs again, does the context switch, and the process continues forever. This whole procedure continues forever, or as long as the machine is powered on. Thank you. Module 2, Concurrency Basics, Topic 1.3, Threads and Go Routines. So we talked about what a process is. Now I want to define what a thread is. So threads versus processes. It used to be that there were only processes. Now, this is way back when Unix was first created, right? They just had processes at first. And they used to say, look, see, one downside of processes is that the context switching time can be long, right? Because the context switch requires taking data, writing it to memory, and then reading stuff from memory back into registers, right? So there's a lot of memory access, and memory access can be slow. So doing a context switch between two processes, that can be slow. And you want the operating system to be fast, don't want to waste time doing that. So switches, the switching process rather, often to speed it up, people said, look, let's make threads. Now they were actually originally called lightweight processes. But what a thread is, it's like a process, but it has less context. Okay, it shares some of the context with other threads in the process. So one process can have multiple threads inside it. Okay, and the threads share a decent amount of context. So if you look at the top picture, I show a process, right? And it's got these two blocks of things that are unique to the process. You know, it's virtual memory, with page table, that sort of thing. File descriptors, you know, it's stack, it's program counter, you know, all these things, it's registers. Those are all unique to a process. Now notice how I separated them into two. I have that little orange block and the green block, right? But all of those are unique to a process. Now that once you start having threads, you can have multiple threads in one process. So you can see the green chunk, the green rectangle as a thread, right? So you can think of that process picture as just a process with one thread in it. Okay, one green thread, and with one code, and each thread is associated with a piece of code that is executing. So the stack is since the stack is associated with the code executing, you got a stack, and you got some registers. Data registers are unique to a thread. But in the bottom picture, what I'm showing is one process with 3 threads inside it. Now, each one of these threads does have unique context, right? The stack is unique for every thread. The code is unique for every thread. The data registers are unique for every thread. So there is unique context between different threads. But they also share context, like that stuff in orange. That's the virtual memory system. That's the same, right? The file descriptors, those are the same. So, you know, this isn't an exhaustive list, these pictures. But the point, though, is that these threads, they have unique context, but it's much less than the unique context between 2 different processes. So when you do a context switch between 2 processes, that might take you a long time because there's a lot of context that's unique. But with 2 threads, when you go from one thread to the next in the same process, it's much faster because there's less context, less data that you have to write to memory and read back from memory when you do a context switch. So, and now what happens in operating systems is that they, instead of scheduling processes, they schedule thread by thread. So they say, okay, this thread runs and that thread runs, then that one. Where in the old days, it used to be process by process. Now they've gone to this sort of thread level granularity. It's the same problem, but the level of granularity is different. They do one thread at a time and they schedule accordingly. Now, Go routines. Now we're moving to Go. All that other stuff that I talked about, it was sort of generic, independent of the particular language. It was talking about operating systems in general. Now we're going to talk a little bit about Go. Go has what are called Go routines. Go routines are basically a thread, but in Go. Many Go routines execute within a single operating system thread. So remember how there was this hierarchy where I said, look, there's a process and it's got many threads in it, right? That's from the operating system point of view. You can have many threads inside a process. Maybe a process only has one thread, what you call a main thread, but it might have multiple threads. Now what Go does is it says, look, it takes a process with one thread in it, one main thread, and you can have multiple Go routines that are all executing in that same thread. So from the operating system point of view, all it does is schedule the main thread. But then within Go, you can have multiple Go routines that are all executing within that thread, all alternating within that thread. So maybe Go routine 1 executes, then 2, then 3. All the while, from the operating system point of view, nothing is changing. It's got its main thread running. But inside Go, Go can start switching basically these Go routines, which are like threads, inside the main thread. So that process of doing the switching, determining which Go routine is executing at what time, that scheduling process, that's done by what's called the Go runtime scheduler. The Go runtime scheduler, it does scheduling within an operating system thread. So you see how the scheduling task is sort of separated between the operating system and the Go runtime scheduler. The operating system schedules which operating system thread runs at a time. And then once the main thread is running, your Go program is running within a main thread, an operating system thread. Once that's running, the runtime scheduler can choose different Go routines to execute at different times underneath that main thread. Now, the Go runtime scheduler uses a logical processor. This logical processor is mapped to a thread. Okay, so typically, like default, you're going to have one logical processor mapped to a main thread. And then the Go routine is going to run on that logical processor, which means it's running in that main thread. Now notice that since all these Go routines are basically running in one thread, one main thread, there is not an opportunity for actual parallelism like this, right? It's all concurrent. You're executing one Go routine or the next at a time. But what you can do, and we'll touch on this later, is you can, as a programmer, you can say, look, I don't want one logical processor, I want two logical processors, or 3 or 4. And you would do this according to how many cores you had, presumably. That would be sort of the obvious way. You might say, look, I got 4 cores, I'm going to have 4 logical processors. Then what will happen is the Go runtime scheduler, it'll take these Go routines and map them to different logical processors. Each logical processor can be mapped to a different operating system thread, and the operating system can map those threads to different cores. So you can sort of allow, there is a way to change the settings so that you don't have just one logical processor, you have multiple. And if you had cores, that would allow multiple cores. That would allow you to exploit those cores during execution. Now, still, this task of hardware mapping, determining this Go routine, which core is it on, that task is still not done by the programmer. But the programmer can determine how many logical processors that are going to be used. So, and by default, it'll be 1, in which case it's got to be concurrent behavior. But you can increase that if you want to, and which would allow the Go runtime and the operating system to do parallel scheduling if it wanted to. Thank you. Module 2, Concurrency Basics, Topic 2.1, Interleavings. So writing concurrent code is hard. And part of the reason why it's hard, a big chunk of the reason why it's hard, is because it's hard to have a mental model of the state of the program at any particular time. So what I mean by that is if you're writing sequential code, regular old code, and it crashes on line 10, then you know what's been executed before that. You know, oh, it must have executed line 9, 8, 7, 6, and so on. And you know basically what order, right? And so it helps you figure out what the state of the program should be where it crashed. And you sort of implicitly depend on that when you're debugging. You say, well, I know it got to here, so it must have done that and that, right? And that helps you zero in on what the problem is. With concurrent code, it is much harder to get a bead on the state of the machine. So when it crashes, maybe it crashes at line 10 in task 1, but where is it in task 2, 3, 4, 5, right? It can be in different places. So the overall state of the machine is not deterministic. Meaning, so by that I mean, say you got a crash, it crashed on line 10 in task 1 every time. But every time it can be at a different point in task 2 or 3 or 4, right? So every time you run it, even though it crashes at the same line in task 1, it may be at different overall system states every time. So it makes it confusing to sort of keep in your mind, this variable should be that and this variable should be that, because maybe this task has done something or maybe it hasn't, and you don't know what's been done, what hasn't, okay? So this is really, to me, the hardest part about programming writing concurrent code in any language. So just to show you, what the complexity is here, you have what are called these interleavings, the interleaving of the instructions in 2 different tasks. So the order of execution of statements in a task is known. So for instance, I got task 1, task 2, and each one has 3 instructions in order, 1, 2, 3, and these are just random instructions. It doesn't matter what they do. But you know that in task 1, the instructions are executed in order 1, 2, 3. Task 2, they're executed in order 1, 2, 3. But the order of execution between concurrent tasks is not known, is not determined, meaning it's non-deterministic. It can be different every time. So what that means is these instructions can be interleaved in different ways. So I might execute the first instruction for task 1, then the first instruction for task 2, then the second instruction for task 1, then task 2, second instruction, so on. But that's one possible interleaving of instructions. But there are many possible interleavings, and all of them could happen. And so every time you run it, you might get a different interleaving. And so it makes it harder for a program to keep in their mind, because you have to consider all these interleavings when you're thinking about the correctness of the system. Now, hopefully not all. There are techniques to sort of minimize it, but you have to consider many different interleavings in order to reason about how the system behaves. So here's an example of a couple of possible interleavings. So on the left column, so I got 2 little tables, right? One on the top, one on the bottom. The top is showing one interleaving, the bottom showing another. The left column are the instructions in the task 1. The right column are the instructions in task 2. Now the top interleaving, the top one is showing, it's just alternating between instructions in one task versus the next. So task 1, instruction 1, task 2, instruction 1. Test 1, instruction 2, test 2, instruction 2, and so on. Now, the bottom interleaving is saying, look, it fully executes task 1, 1, 2, and 3, and then it fully executes task 2, right? 1, 2, and 3. That is possible too, and there are many more. So there are many interleavings that are possible, and you have to consider all these possibilities, or at least some subset of these possibilities, when you're thinking about does your code work correctly or not. Now, one other thing that I'd like to mention is that these interleavings, the interleaving problem is even a little more difficult because the interleaving doesn't happen at the level of the C code or Go code, right? So you write these instructions. Let's say these are Go instructions, right? So the interleaving isn't happening at the Go instruction level. It's happening at the machine code instruction level. So what I mean by that is that first instruction, A equals B plus C, that, in Go, maybe that's all it is. But if I were to look at the machine code for that, that might be, 4 instructions long. I might be doing a load B from memory, load C from memory, add them together, and then do a store A, right? So it might be 4 machine code instructions long. And the same thing with each one of these instructions. So the interleaving is happening even at the machine code level. So what that means is you're not guaranteed that it finishes instruction 1 in task 1 before it starts instruction 1 in task 2. So take that A equals B plus C in the top interleaving, right? The first line in task 1. Say that takes 4 instructions, 4 machine code instructions. You might execute the first 2, and then it stops and goes to task 2. Right? So you might not even finish the first instruction. So these instructions, the interleaving is happening even in between these instructions because it's happening at the machine code level rather than the source code level that we're looking at right here. So that makes it even harder to sort of get a handle on all the possibilities. Thank you. Module 2, Concurrency Basics, Topic 2.2, Race Conditions. So a race condition is a problem that can happen as a result of all these possible interleavings that you have to consider. Race condition is technically it's usually defined as a program that runs a problem where the outcome of the program depends on the interleaving, right? Now, the interleaving, remember, is non-deterministic. It's determined by the operating system and the Go runtime. So the interleaving can change every time you run it. And in a lot of ways, it has a lot of freedom. And so you have basically a non-deterministic interleaving. But you never want a program, or almost never do you want a program whose result is non-deterministic. Okay? You want it to be that if you run a program and you give it a set of inputs, it always produces the same outputs. Okay? That's determinism, right? If a program is non-deterministic, you take that program, you run it with a set of inputs, sometimes it gets one answer, sometimes it gets another, that is almost always a failure. Okay? That's non-determinism, and you don't want that. But remember that the interleavings are non-deterministic. You don't know what the interleavings are. So you have to make sure that your program, that its outcome does not depend on these interleavings. If it does, that's called a race condition. So what I'm showing here is a little example, just toy. We got these 2 tasks, and we're showing 2 different interleavings of the 2 tasks. Now the first task, all it does is instruction 1 says x equals 1, and instruction 2 says x equals x plus 1. Okay, so real simple. And on the right-hand side, you got task 2, and all it does is print x. Now, in the first interleaving on top, it's going to print a 1, because x is set equal to 1 at the time when the print happens. Where in the second interleaving, x is going to print a 2. X will be printed as 2 because it's a different interleaving. This is a race condition. The outcome depends on the interleaving, and the interleaving is non-deterministic, so this thing has non-deterministic output, and that's basically broken. Now, so this needs to be avoided. This is one of those complexities that happens because of all these interleavings. Now, race conditions, there are ways to avoid this type of thing to make sure it doesn't happen, and we will talk about that in Go. Race conditions occur due to communication between tasks, or Go routines that we're going to talk about. So there's communication between these 2 tasks. I don't know if you see it, but they're communicating on variable x. So the one task on the left, it's writing to x. It's assigning x to 1 and assigning x to x plus 1 to 2. Where the other task on the right is reading from x. It's reading from it and then printing it, right? So they are communicating through this shared variable called x. And that's communication, and that's where race conditions occur. See, if you had no communication between two different tasks, you would never have a race condition because the ordering would be completely independent of each other. But, meaning, when I say completely independent, the outcome would be completely independent of the ordering of the interleaving. Okay? But when you have some kind of communication going on between the two, then it matters which instructions in task 1 say, which instructions that write to this shared variable, which ones happen before task 2 reads from the shared variable. So communication is sort of the source of race conditions, but communication is very common between these different Go routines. So different tasks, they generally communicate. Now, threads in general, whatever language, threads are largely independent. Okay, they're independent of one another, but not completely independent. So what does that mean? They're largely independent, meaning they mostly don't have to communicate with each other, right? The whole reason why you've made two different threads, or Go routines as we're going to call them in Go, the reason why you've made two different threads is because you feel like these two things can be executed concurrently at the same time, right? Without caring like which one executes first or second. They can just execute at the same time. But they're never completely independent, because if you got multiple threads all in one process, they're sharing information, right? Remember how threads they share common data, right? They share the virtual space and all this. There's the fact that they're different threads in the same process means that they are sharing. So it's very common that there's some level of sharing between the threads, and the sharing of information is communication. So, for instance, web server is a really common sort of multi-threaded application. So in this picture of the web server, you got in the middle, you got this web server. Now on the right, you got these clients. These are web browsers, okay? And they're connecting to the web server over the network. And I'm showing 3, but there can be any number of them. Then on the left, I've got the web page data, right? So this web server, say it's UCI's web page, it's UCI's web server. It's that orange data is all the data on all the pages that we have. Okay, and that's going to be together with the web server and some disk or something, right? Now, as these clients come in, as they make connections, so one browser comes to the website, it wants to look at one page. Another browser connects, it wants to look at a different page, different sub-UCI page. Another client comes in and wants to look at a different one, right? So this web server program, it makes a lot of sense for it to make a thread for every client that comes in. Because each one of these communications, like if this communication with one particular client, it's likely to do different things. This client, maybe it wants to look at this web page, where the next client wants to use another web page, right? All within UCI, but different subpages. So it makes a lot of sense. Oh, and to do them as multiple threads, because these clients are all coming in at the same time. So it's the type of thing where you have to handle all these clients all concurrently. Right? You need to handle, you don't want to have a web page that handles one browser at a time, right? You got to handle them all concurrently. So it makes a lot of sense to make this a multi-threaded application. You got one thread for each client. Now, these threads are largely independent, but they do share data sometimes. You can have two clients come in and look at the same web page, right? They might both be looking at the top of the web page. Also, you can notice these arrows between these blocks are two-way. So, for instance, you can have a web page where the client sends data, basically posts data to the web page. We don't want to get into web page too much, but the client may post data to a web page, actually changing the web page. Like the most obvious place where you see this is sometimes you see a web page where it has a counter, like a visit counter, right? That data is changed every time a client connects. The counter goes up one, right? So that counter value. Say there's another client who comes into that same page. He's got to see the updated counter value. Right? So in this way, one client is writing to the web page, increasing the counter value, and the next client is reading from that same page, reading the new counter value, and then writing back to it, increasing the counter value again. So the point, though, is that there is some level of communication between these clients. They're not completely independent. They can be looking at the same subpage, looking at the same files and data, and so on. So periodically, they have to communicate with each other. So now, it shouldn't happen too often. If there's too much communication between two threads, you probably don't have them in separate threads. If they're communicating all the time, then you should probably just make them one Go routine. Don't separate them. But if they're separate mostly, but every once in a while having communication, then two Go routines makes a lot of sense because they can execute concurrently most of the time. Now, another example I have is this image processing example. So image processing tasks are often what they call embarrassingly parallel. So image processing, say you got some big image. You got some images, I don't know, a megapixel, okay? It's got 1,000,000 pixels in it. And you want to do some processing. You want to do a blur or something like this, okay? Maybe you want to blur the pixels. So with a blur, basically it's a pretty localized operation. You look at a pixel, you look at the surrounding pixels, you average out the values. But this same task, you got to do it on every single pixel, right? So this type of thing, it makes a lot of sense to have multiple threads. You got one thread dealing with some pixels, another thread dealing with the next set of pixels, another thread dealing with the next set. I'm only showing 2 threads right here. Actually, this is, in an extreme, this is what a GPU does, a graphics processing unit. This is exactly what a GPU does. You might have 1,000 cores on this GPU, and it'll take an image with 1,000,000 pixels, and they'll just divide up all the pixels, right, between the different cores that are all running on different threads on each core. So this is a common thing where it's easily parallelizable. You know, one thread can work on one set of pixels, one can work on another, but not completely parallelizable, because take like a blur. A blur, you're analyzing a pixel, you got to analyze the neighboring pixels and average their values. So you are not completely independent of the neighbor, right? If there's another thread working on your neighbor pixel, those two have to share information, right? This guy has to know the pixel value on the neighbor. This guy has to know pixel value on the neighbor. So there is some communication between these threads. They got to share whatever their pixel values of the neighbors have to share. So even though image processing is, you can largely parallelize it and chop it up amongst different threads, there's always some level of communication between the threads, and you have to be able to support that. And remember that this communication, if you don't support it correctly, it can be the source of race conditions, where, if one happens first before the other one, it's some weird interleaving, you get different results. So this is part of what makes concurrent programming very difficult. Thank you. Module 3, Threads in Go. Topic 1.1, Go routines. So in the previous modules, we've been talking about concurrency and parallelism, and how processes work and threads work, how they execute concurrently at least, and maybe in parallel if you have extra hardware. But we haven't really talked about how you actually implement that, certainly not in Go, but how you implement that in software. So in order to get these multiple threads, we're specifically focusing on threads. In order to create these threads of execution, you have to use certain programming constructs that are built into the Go language. And this is one of the advantages of Go, that it has a lot of these constructs built right in, and they're easy to use. So say you want to create a Go routine, right, which is a thread that can run concurrently with the other Go routines. Now, one Go routine is always created automatically to execute the main. So even if you don't do anything special, you run a main, it will create a Go routine and execute the main inside that Go routine. Other Go routines are created using the Go keyword. So as an example down here on the left, we have an example where there's just the one Go routine main. Okay, so this is some segment of main, right? A equals 1, you call foo, A equals 2. That's just main. That's one Go routine, the main Go routine, executing all 3 of those instructions. The fact that foo is a function call. Now on the right is the version where we actually create a new Go routine just to execute that function foo. So you can see on the right, there's A equals 1, that's executed in the main Go routine. Then we say go foo, that creates a new Go routine which will execute the code in foo. And then we say A equals 2. A equals 2, again, is still in the main Go routine. So after you call go foo, there are now 2 Go routines, the main Go routine and this newly created, let's call it subroutine, Go routine that's created. And notice it on the right. So on the left, the main will block when it comes to foo. When I say block, the main will, so there's A equals 1, then foo, then A equals 2. A equals 2 can't execute on the left until foo is complete, right? So foo will, it's not blocking, but foo has to completely execute before A equals 2 can happen. That's on the left. On the right, where you have the extra Go routine that you've created, you say A equals 1 in the main, then go foo, it creates this new thread or a new Go routine to execute foo, and then A equal 2 can execute while foo is going on, or before foo's even started. We don't know the timing. It depends on the scheduler, on the runtime Go runtime scheduling, how that's going to be scheduled. But A equals 2 does not. It can execute immediately. It doesn't have to wait for foo to complete or anything like that, because foo is being executed in a concurrent Go routine. So I just showed you how to start a Go routine. It's pretty simple. You say Go and then give the name of the function that you want to execute, or define the function you want to execute, and the Go routine will execute the code associated with that function. So a Go routine generally exits when its code is complete. Okay, so whenever it's done with whatever function it's executing, it's done. It returns from that. Then the Go routine just exits. Now, when the main Go routine is complete, all other Go routines are forced to exit. So what that means is you start with the main. You can make several Go routines from the main. But even if these other Go routines are not finished with their code, if the main Go routine ends, then all the other Go routines will be forced to end and will be forced to exit. And this is important to understand, to think about when you're writing your routines, because what will happen is the Go routine that you create may not complete its execution because the main completes first. And so you might get this behavior where you say, look, I wrote this code and this Go routine is supposed to execute, and it doesn't seem like it's executing. And that might be because the main is completing before the Go routine ever got to finish its own code. So that's something to watch out for. Thank you. Module 3, Threads in Go. Topic 1.2, Exiting Go routines. So we already described how Go routines will exit when they complete their code. But also, Go routines will be forced to exit if the main Go routine exits early. Then all the Go routines that are created, they all are forced to exit. So they might exit early before they do their job, right? Before they finish their job. So I'll give a little example, a piece of code here. And by the way, in these code segments, I'm generally clipping out the importing the packages, right? So I have to, in order to use this program, I have a printf, right? I'm using the FMT package. So I haven't put the part in there where I import that, but assume that that's there. I just want to get right to the Go routines. So in this main, it's pretty simple. It first thing it does is it creates a new Go routine, which should just do a printf rather, and print new routine. And then after that, or not, we don't know the order, but at some other point in the main Go routine, format.printf main routine. So you expect to see two things printed on the screen, main routine and new routine. And you wouldn't necessarily know what order these two are going to get printed in, right? Because when the Go routine is created, we don't know how the scheduler is going to schedule the main routine and the Go routine. Maybe it schedules the Go routine first, the new Go routine first. Maybe it schedules the main Go routine first. We can't really tell. But at a glance, you would expect it to print main routine and print new routine at some point in some order. But when I execute this, only main routine is printed. So why does this happen? It's because the main Go routine is finishing before the Go routine, the new Go routine starts. Okay, and this happens consistently. So theoretically, we don't know how the scheduler is going to work. The Go runtime scheduler, we don't know, is it going to let the main Go routine run first or the new Go routine run first? We don't know. So theoretically, if you ran this over and over, you could get different ordering, right? You would think, well, sometimes the main goes first, so it does main routine and then it quits. Sometimes it does the new Go routine and then it prints new routine and main routine, right? Maybe. Actually, what happens is when I run this anyway, every time it just prints main routine and quits. So what I assume from this is that the scheduler, the Go runtime scheduler, is giving preference to the main routine. So it's always letting the main routine go first before the new Go routine. I don't know that for a fact, but it seems like that's how it's implemented. But even if that's how it's implemented, we have no definite knowledge of that. Meaning, maybe it's implemented in that way right now, but then in the next version of Go, they might change the scheduler so it does something different, okay? So that's not something that ordering, we can't rely on. We have to assume that we have no idea what order the scheduler is going to work in, what order it's going to execute these Go routines in. So definitely though, what's happening here is not what I wanted, right? It just printed out main routine, never printed out new routine. So I got to get this main so it doesn't exit so early, right? I don't need it. I don't want main to exit so early. I want main to somehow wait for the other Go routine to exit before it, so that I can get the new routine to be printed out, right? So how should I do this? So first I'm going to show you this one way, which is really a hack, but I'm going to show it to you anyway, okay? Just so you know what not to do. But it works, it works sometimes, but it's not a safe thing to do. So here's what I do. What I do is I just added this line that I highlighted in red, time.sleep. So, and I give it 100 milliseconds. So what I'm doing is I'm And notice that time.sleep, it executes in the main Go routine, not in the new Go routine that I created, in the main Go routine. So I create the new Go routine, calling Go. Then I put the main Go routine to sleep for a little while, 100 milliseconds, and then I have the main Go routine print main routine. Now what that does is, in that time that the main Go routine is sleeping, the Go runtime scheduler isn't stupid. It's not going to just let the machine sit like that when it knows it has another Go routine available, right? Because remember, a big benefit of doing concurrent programming is that when one Go routine or one thread is blocked and waiting for something, then the scheduler can just move in another one. So it doesn't have to waste time. It can say, look, I've got another available Go routine. Let me schedule that. So that's exactly what's happening here. When you put the main Go routine to sleep, the main can't run, so the scheduler, the Go runtime scheduler, schedules in the new Go routine that it created, that I created just before. It prints out new routine, and then main routine printed out. So what I get printed now is new routine, main routine, just like that with no space, because I didn't put a space or character turn or anything. But that's what I get. So this is my hacky attempt to get the Go routine, the main Go routine, to stay alive long enough for the new Go routine to actually complete its execution. And it works. It works pretty consistently on my machine. But this is not what you should do, but this worked. You can see how this worked. So doing what I did, adding a delay like that to wait for a Go routine is bad, bad, bad. Reason why is because you're making assumptions about the timing, and your timing assumptions may be wrong. So in this case, the big assumption I'm making is that the delay of 100 milliseconds, which I injected in there in the main Go routine, I assumed that will be enough to ensure that the new Go routine has time to execute. So I assumed, look, I assumed a certain behavior of the scheduler too. I said, look, if I force the main to delay for 100 milliseconds, the Go runtime scheduler, of course, is going to schedule this other Go routine that I've created, right? I assume that. I don't know that, right? I don't know how they've implemented that, but I assume that. And so I assume that the Go runtime scheduler is going to schedule the particular Go routine that I had in my mind. Also, I'm assuming something about the operating system too, because for all I know, the operating system, which is running above the Go runtime, it could take that 100 milliseconds and move in another thread entirely. It might just, so right now I've got, if you remember, there's a thread, an OS, an operating system thread, that all the Go code is running in, right? All the Go threads are running within this one operating system thread. The operating system might just say, look, I'm going to take that thread and put it out, context switch it, and bring in an entirely different thread. Maybe it'll bring in PowerPoint or something, which is running on this machine, right? So that it might use that 100 milliseconds in a way that I don't anticipate. Now, it doesn't, and there are reasons why it doesn't, but I'm making certain assumptions about how the operating system scheduler works and about how the Go runtime scheduler works. And these assumptions are not safe to make, right? I have to, because these can change in different versions of the operating system. So relying on timing like this is not safe. The timing is non-deterministic, meaning every time you run the program, the timing might be different, and you have to assume that. Because if you don't, what will happen is at some point, you get these really bad intermittent errors where most of the time it'll work, but sometimes your timing assumption will be violated and sometimes the error will happen. And these are the worst. These are one of the worst types of errors because then you get these intermittent errors which only happen occasionally. So you run it and you say, oh, I found a bug. Let me run it again to reproduce it so I can debug it, and you can't, right? You run it again and again and again and the bug doesn't happen again. Those are terrible types of errors to have to debug. So this is not what you want to do. You don't want to rely on timing. Now, I have a long story, which I could talk about, where I relied on timing as an undergrad and failed badly in a big assignment, but I won't bring that up. It's kind of interesting, but it's sort of off track. Still, you can't rely on the timing. So you need formal synchronization constructs, and we'll talk about those. Thank you. Module 3, Threads in Go, Topic 2.1, Basic Synchronization. So synchronization is when multiple threads agree on the timing of an event. Okay, so you have these global events. Synchronization means you synchronize on these global events whose execution is viewed by all threads at the same time, so they can agree on the timing of this particular event. Now, why this is interesting is because in threads, using threads and Go routines are basically threads. So when you're using Go routines, they typically, one Go routine doesn't know anything about the timing of its neighboring, of its fellow Go routines, right? So if a Go routine is executing some code, it knows what line of code it's at. It doesn't have any idea what line of code the other Go routines are at, and it doesn't care because, for the most part, because they are largely independent, not completely, and we'll get to that, but largely independent. So normally these Go routines don't have any understanding of the timing going on in the other Go routines. But synchronization basically breaks that. Synchronization says, look, we're going to make some kind of a global event that every thread sees or every Go routine sees at the same time. And these are important to restrict ordering, restrict some of the different interleavings that are possible. Okay, so let me I got this small example here where we're ordering relative ordering between two different Go routines, or two different threads in this case, it's actually very important. And so it's important for them to synchronize on certain events. So just to explain this picture, I got this on the left. I got a left column and a right column. I got two little tables, right? One on the left column and the right column. Left column is one simple thread, and it doesn't do much. It has two instructions: x equals 1, x equals x plus 1. Very simple. And then on the right, that thread just does one thing: print x. Now, what I'm showing here in these two different tables, one on the top, one on the bottom, I'm showing two different possible interleavings of the instructions. And there are other interleavings, but I'm just showing two. So in the top one, the print x happens after the first instruction in the left thread, but before the second instruction. So if you print x at that point, x is going to equal 1. Where if you look at the bottom, you got this time in this interleaving, the print x happens after the second instruction on the left thread. So at that point, x is going to equal 2. So what I'm showing you here is basically a race condition where the output, what's printed, is going to depend on the interleaving of the instructions. Okay, and the interleaving, remember, is non-deterministic. It is determined or when I say non-deterministic, in reality, it is not non-deterministic. There is a Go runtime scheduler, there's an operating system scheduler, and they are deterministic programs. But from our point of view, it is non-deterministic because we don't understand their algorithms. We don't know if weird things like interrupts are happening and things like this that can alter the scheduling. So from our point of view, the scheduling is non-deterministic. So we don't know, as a programmer, we can't tell which one of these two interleavings it'll execute. And remember, every time it might run a different interleaving. One time it might run the top, one time it might run the bottom, and so on. Now, let's say, so we have to understand, in order to understand what the correct operation of this little program is, we have to know what the intention of the programmer was. So let's assume that you want to do the print, you want the print to occur after the update of x, after the x equals x plus 1. So that means the bottom interleaving is okay, but the top one is bad. So but remember that since we have no control over their relative ordering, that's all up to the scheduler, we can't control which one of those two happens. Well, synchronization allows us to control that. Okay, synchronization, we're going to use synchronization to make it so that the top interleaving is impossible. Right? And in order to do it, we need some kind of a global event, some sort of event, and there are lots of different forms of this, which we'll get into in later modules. But we need some sort of a global event that both of these threads see happening at the same moment. And then we can have conditional execution. We can say, one of them can say, look, if this event happens, then I execute, else I wait. Something like that. So let's show that right here. So here's my simple synchronization example. I got those same two tasks. The task 1 on the left, it just does the x equals 1, x equals x plus 1. Task 2 on the right, it does the print x. But notice I've got this global event now. So I didn't specify what the global event is. We'll get to that later. But in task 1, after doing x equals 1 and x equals x plus 1, it executes this global event, okay? Whatever it is. So that event is seen by all tasks, all threads, including task number 2. And in task number 2, it says if global event has happened, then print x. So what happens here is that print x in task 2 can't happen until the global event has happened in task 1. So that has restricted away some of the possible interleavings. Now the print x has to wait until after x equals x plus 1. Right? You can see that x equals x plus 1 has to happen first before the global event, and print x has to happen after the global event, and so the ordering is restricted. So this is an example of synchronization. Now we need this synchronization in an example like this because of our intent. We needed this print x to happen at a certain time relative to the print x in the task 2 has to happen after certain instructions in task 1. And there are examples like that. Actually, we'll come up with more of these examples in a later module. But there's many examples like that where certain events have to happen in a certain order. Now notice that this is the opposite of concurrency, right? So concurrency, the beauty of concurrency and parallelism is that the interleaving is arbitrary. In fact, if it's parallel, things can run at exactly the same time, but even if it's not parallel, if it's just concurrent, the ordering is arbitrary. We don't care about the ordering. And that gives us a lot of advantages. It allows us to speed up the execution of the code. Like with concurrency, if a thread is ever blocked waiting, then since the order doesn't matter, the scheduler can just move in another thread in the meantime while the first one's waiting, right? So we get a lot of optimization, a lot of speed improvement because we're not restricting, when we don't restrict the scheduling. But by doing this, by using synchronization, we are restricting the scheduling. So understand that every time we use synchronization, we are reducing the efficiency. We're reducing the amount of possible concurrency. So we're reducing the options for the scheduler, so the scheduler won't be able to use the hardware as well as effectively. So there might be times when nothing can execute because we're waiting on these synchronization events. So in general, synchronization, it's bad because it reduces your performance and your efficiency in general, but it is necessary for cases like this where you have to restrict the ordering. Certain things have to happen in certain orders. There are a lot of tasks where that's the case, and we'll bring up more examples like that. So synchronization is necessary evil. And I'll also mention that it is complicated to use. It can be, although GoLang makes it pretty easy. It has pretty straightforward constructs, so it's easier to use in GoLang than it might be, say, in pthreads or something like that. But anyway, this is an example of synchronization. It is bad but necessary. Thank you. Module 3, Threads in Go. Topic 2.2, Wait Groups. So wait groups are a particular type of synchronization that are common. So we're going to start talking, right now we'll talk a little bit about this sync package. Sync package, you have to import that, but sync package, it includes wait groups. Wait groups are useful for synchronization. We're going to cover other parts of the sync package later, but right now let's use wait groups just to deal with the problem that we were dealing with earlier about the main ending early before the go routine that the main started gets to finish. So the sync package has a lot of different synchronization functions built into it, synchronization methods. But sync.waitGroup, what that does is it forces a go routine to wait for other go routines. So a wait group is basically a group of, you can think of it as a group of go routines that your go routine is waiting on. And your go routine will not continue until all those ones that are in all the go routines in the wait group, until they've all finished. So this is what we need for for the example that we had before. Remember that print a message, and then I had the new go routine print a message, and the new go routine's message never got printed because the main go routine executed and completed before the new go routine had a chance to execute, and then that forced the new go routine to exit, and it never got to finish. Okay, so what we want to do is make this main go routine wait until the new go routine that is created, until that finishes. Okay, until that exits. Then the main go routine can continue. Okay, and in that way, we make sure that this new go routine has a chance to actually execute before the main go routine completes. So that's what we want. We want to have a go routine, in this case our main go routine. We want to wait on another go routine. Now, wait group is a general function, general set of methods, general object with a method that allows you, a set of methods associated with it. You can wait on a lot of different go routines if you want to. So you could have one go routine waiting on 10 different go routines and wait till they all complete. In our example, we're only going to wait on one, but understand this is generalizable, so you can wait on as many as you want. So this sync.waitGroup object, it contains an internal counter, often called a counting semaphore, but just think of it as a counter. It starts off at 0, okay? You increment the counter for each go routine you want to wait for. So if there are 3 go routines you want to wait for, you increment the counter 3 times, so make it 3. Then you decrement the counter when each go routine completes. So if the counter is up to 3, you're waiting for 3. Every time a go routine completes, it goes down from 3 to 2, 2 to 1, 1 to 0. Now the waiting go routine that's waiting for these 3, it can't continue until the counter is down to 0, which means that all the different go routines have all completed. That's the idea of how the sync wait group object works, and it's got a set of methods associated with it that allow this to happen. So let's take a look at something like what it does. So in this case, I'm trying to depict 2 things. On the left sort of column there, labeled their main thread, that blue up vertical set of lines. That's the main thread. And then the right is this foo thread, which is the new Go routine that the main Go routine has created. Okay. So I'm just showing a little bit of the code execution. Actually, first let me go down to the bottom and name these methods that are associated with wait group so we understand what they do. So there's an add method, a done method, and a wait method. Add method increments the counter. Okay, so remember I said there's this counter and you increment it for once for everything that you want to, for every Go routine that you want to wait for. So add does that. So you can say add, pass an argument 3, it'll add 3 to the counter. Now done decrements the counter. Okay, so done is what's executed at the end of each Go routine. Each one of these Go routines that the main Go routine is waiting on, they need to execute a done at the end to decrement that counter back down. And then once all of them have decremented the counter down to 0, then the wait will continue. So the wait is called inside the main. Okay, and what will happen is that wait will block until the counter is equal to 0. So if the counter is equal to 1 or anything greater than 0, that means that some of these Go routines that you're waiting on are still executing, which means you have to wait. So it'll just block until that counter eventually gets down to 0 because finally all the Go routines have executed the done. And then you once it gets down to 0, the main will continue. It'll go past the wait will complete, and you can continue. So if we look at the picture now, I'm just showing a sort of a sketch, trying to highlight the important parts of the routine of the main thread, for instance, and the foo thread. So in the main, first line up there, I'm saying I'm creating a WG, a variable called WG, and it's a wait group. And then first thing I do with it, you see highlighted in red, I say wait group WG.add1, because I know that I want my main thread to wait for one Go routine. So I add 1. Then I create the Go routine, go foo, and I pass it, in this case I pass it the wait group. Now it needs the wait group because remember that the foo thread, the new thread that I'm creating, it's got to call done on that wait group, right, to signify that it is complete. So, okay, but let's stick with the main thread for a second. So the main thread, it creates the foo, the new thread, go foo, and then it calls wait. So it says wg.wait. Now at that point, it's going to block on that line until this foo thread that we're waiting on actually completes. Now then go over to the right, the foo thread. It is created. You can see when go foo is called, it creates a new thread. So you see that red vertical line, right? That's the foo thread. So the foo thread does whatever it's supposed to do. I don't know what code it has in it. It doesn't really matter. But at the end, whenever it's done, it calls wg.done. And that will decrement the wait group, the counter inside the wait group. So now, like in this example, I added 1 to the counter, so the counter is equal to 1. I added that in the main. In the foo thread, once it's done, it decrements it by calling down. So at that point, when it calls down, the counter in the wait group should be equal to 0. And then the wait, the WG wait function call that was called inside the main thread, that will continue, that will complete, and the main thread can continue with whatever code it has to execute after that wait. So this is an example of how wait groups used. In this case, we're only waiting on one thread, this foo thread, one Go routine. But we could wait on any number if we wanted to, just by adding. If we wanted to wait on 10, we'd add 10, right? And then each one. Now, remember, as a programmer, you got to make sure to use these methods correctly. So you got to put the wg.add in your main or in your Go routine before you want to wait. And it has to be incremented to the value of which is the number of Go routines you want to wait for. You've also got to make sure that each one of these new threads that you're waiting on, that they all call done, the done method on this wait group at the end when they are finished. And they got to wait till they're finished, okay? It can't do it earlier. It's got to be, so a lot of times people will use a defer to make sure that it happens at the end. And then you've got to make sure as a programmer that in your main or in your whatever the waiting Go routine is, like in this case it's main, but whatever the waiting Go routine is, you call wg.wait. If you don't call wait, then none of this will then there won't be any waiting going on. So you got to, it's up to the programmer to inject the add, the done, and the wait at the right places to make this whole mechanism work. So here's a little example of slightly modified example of that print problem that I had, the print assignment where I wanted the simple version. I just had the main create the foo. It's actually, you can see it here. If you look at the main function, in the middle of it, it says go foo, right? So it creates a new Go routine that executes foo. But I've added some code. So after that, it's supposed to print main routine, and the foo is supposed to print new routine. So I've added a few things. Like if I look at foo, it prints new routine, but I add this line, it says wg.done, right? So it has to call done. That was the thing that I had to add. So I add that. Also in the main, things that I've added are, I define the wait group, var wg sync.wait group. Then I say wg.add1, right? So before I create the go routine, I add one to the wait group, because I know there's going to be a new one go routine that I'm waiting for. Then I create the go routine with that go foo, and then I call wg wait after that, so that my main will actually wait on the go routine to complete, and only after that that foo go routine has completed will it continue on and print main routine. So in this way, my main won't just end early and cause the foo go routine to never complete, right? Now the main has to, it won't exit and won't print main routine until after the foo go routine has already completed and done its job and printed new routine. Thank you. Module 3, Threads and Go. Topic 3.1, Communication. So far we've been talking about creating go routines, a little bit of synchronization, so waiting on go routines to exit. But go routines also communicate sometimes. So generally, go routines work together to perform a bigger task. So these go routines are not completely independent, typically. So typically, you're making a bigger program that has sort of semi-independent pieces. Each go routine does one of these semi-independent pieces, but they are not completely independent. If they were completely independent, they'd be entirely different programs, right? You wouldn't even call them the same program, right? You just have a different program. But they're usually doing a smaller piece of a bigger task. I mean, just as an example of something where you might use go routines, say you're making a web server. Web server, it's very common to make them multi-threaded because what happens is this web server, it might be handling, you never know how many people are going to connect to the web server at a time, right? So for each person that connects to the web server, there's an interaction. Each person, meaning each browser that connects, you got to communicate with it. Receive its message, respond to its message, and so on. There's basically a conversation that the server has with each different browser that connects to it. So it's nice to make it multi-threaded, because what can happen is maybe there's 1,000 different browsers connected to this web server at the same time, looking at different pages, different pieces of the page. So it's nice, since they're all doing the same basic type of interaction, right? They're all talking HTTP, sending HTTP message back and forth. It makes sense to have a multi-threaded program, so every time a new connection is made, a new browser connects, you create a new thread for that to handle that connection, to handle the communication back and forth between that browser. And then a new browser connects and you make another thread to handle that, right? So it's a convenient way to keep the state separate, right? Because the state of the communication with one browser can be completely separate or largely separate than the state of communication with another browser. So you want to be able to separate them into different threads, but remember that they are not completely independent. So remember that, like with this web browser idea, all these 1,000 connections that are made, these 1,000 different threads that are running, they're all serving the same set of pages, right? I mean, say this is UCI's web server, right? It's all UCI's web pages they're serving, so they're sharing data, right? Basically, the UCI web page data, they're sharing that, and say one browser might post some data to a web page, and then another browser should be able to view that, right? So there's interactions between these threads since they're all sharing this web page data. So this is sort of a typical scenario where these Go routines, they're not completely independent. They work together periodically to perform some bigger tasks. They have to trade information. So they need to send data and receive data in order to collaborate. So I'll give you just a sort of a toy example. So rather than the big web server example, I'm going to work with something small just to sort of get the point across. So say you got this problem, you want to find the product of 4 integers, okay? And you decide, I want to do this with 2 Go routines. I'm going to have 2 Go routines multiply 2 of the integers. Then, one Go routine multiply 2 integers. The other Go routine multiply the other 2 integers. Then both of those 2 Go routines will send their results back to the main Go routine. And the main Go routine will multiply their results, and the final result will be the product of all 4 integers. So in this case, I've really got 3 Go routines. The main Go routine, plus I'm going to make 2 more Go routines that are going to do sub-problems, right? Multiply 2, multiply the other 2, and the main Go routine combines them. So in order to do this, you're going to need to send data, specifically integers, from the main routine to the 2 subroutines, right? So these 2 new Go routines that you created, you got to give them the 2 numbers that you want them to multiply, right? So data has to go from the main Go routine to the subroutines, sub-Go routines. And then the results of these Go routines, of these sub-Go routines, have to come back to the main routine, right? Because main has to get those pieces of data and multiply them together to get the final result. So you can see the data transfer that's going on between these Go routines. And this is pretty straightforward. This data communication that we're talking about is sort of the most straightforward kind, where the data communication is going on at the beginning of the execution of a Go routine and at the end. Meaning, with these subroutines, these sub-Go routines, they get data right at the start, the initial data, the integers they want to multiply, and then they send results back at the end. So this is sort of the simplest type of communication. But note that the communication doesn't just have to happen at the start and the end of a Go routine. They can happen right in the middle. So in the middle of one of these Go routines, it might decide to send some data back to the main routine. Okay, in a more complicated example. Right now, we're just dealing with the sort of simple version. Right at the beginning, you're sending the Go routines data, and at the end, you get some back. You need communication to be able to do something like what I'm saying here. So communication between Go routines is done using channels. Channels are used to transfer data between Go routines, and channels are typed. So you when you create a channel, you create it with a certain type. So maybe this channel handles integers, this one handles strings, this one handles a structure of a certain type, and so on. So they're typed, and they transfer typed data. So you use make to create a channel. So an example here, I'm making a channel called C. I say C equals make chan int, so that just creates a channel of type int, which transfers integer information. Now, once you got this channel C, you can send and receive data using this arrow operator. So when I say arrow, it's literally a less than and a dash, which looks sort of like an arrow. And so you use this arrow operator to send data on the channel and to receive data from the channel. So on both ends, you send and receive using this operator. So an example here, send data on a channel. Say I got my channel C I just made. I want to send the integer 3. So I write C arrow 3. And so the 3 is, if you follow the arrow direction, it goes into the C. So this thing on the right is going into the channel C. So that's how you would send data on a channel. And you can receive data from a channel. You can see that here. So in this case, the arrow is actually leaving the channel, right? So x equals, colon equal in this case, x equals arrow C. So the data comes out of the channel C, the arrow sends it into the x. So that's how you read it. So you can send data on a channel and receive data from a channel using this same arrow operator. So here's a little example of that code that I just explained, where I want to do this multiplication of 4 numbers. And to do it, I'm going to make these 2 Go routines. Each Go routine is going to just multiply a pair of numbers. And I'm going to start those 2. So the main routine will start those 2, have them multiply pairs. And then the main routine will take their results and multiply those together and print it. So let's see. Let's start with the function prod, right, for product. And basically that just takes 2 integers, v1, v2, and it computes their product. Now the third thing that it takes is the channel that we want to communicate on, right? So it takes that as an argument, and then what it does is it takes v1, it computes v1 times v2, computes the product, and then sends it onto the channel. So now we look at the main. The main, we create the channel, C. We then it starts the 2 Go routines. So go prod, passing them different hard-coded numbers in there. That doesn't matter, but hard-coded 1 and 2 to the first Go routine, and a 3 and 4 to the second. Notice that they're both getting the same channel in this case. They're both going to communicate on the same channel. So it starts the 2 Go routines. Then the next 2 instructions just receive the results from those 2 Go routines on the channel. So A equals arrow C and B equals arrow C. So A gets whatever comes on the channel, the first thing that comes on the channel, and B gets the second thing that comes on the channel. And then I just print, then the main Go routine just prints the product, A times B. So this is an example, a sort of simple example of how you use channels to communicate. Now one thing before I go on is, I said that channels are used to communicate, to send data back and forth between Go routines. And that's true, and we're using it here. But there's another way to send data between Go routines. Certainly when you create the Go routine. When you create the Go routine, so here where I say go prod 1, 2, C, go prod 3, 4, C. I am sending those 2 Go routines the data, which are the arguments to the function. So like go prod 1, 2, C. I'm sending that Go routine through those arguments, the 1 and the 2 and the C, the channel. So that's another way that you send data to a Go routine. And that just works when you start it. When you pass arguments to its function, those arguments are passed to the Go routine. Okay, so I'm sending data, say with the Go prod 1, 2, C, I'm sending 1 and 2 and C to the new Go routine I'm creating, and I'm not using a channel. Okay, so that's another way to send data, and that's sort of common, but that's just initial. Anytime after the starting of the Go routine, if you want to send data back and forth, you have to use a channel, like we do here, where we receive the results on this channel. Thank you. Module 3, Threads in Go. Topic 3.2, blocking on channels. So by default, a channel is called unbuffered. When you create a channel, it's unbuffered. And unbuffered channels cannot hold data in transit. So the default is unbuffered. So when we call make and we say, make and pass it, say chan int, and we don't pass it any other arguments, then we're making a channel that holds integers, but it's unbuffered. So it can't hold data in transit. So the implications of that are that, since we don't want to lose data, the transmission, the sending has to block. The sending instruction has to block until the data is received on the receiving end. And the receive instruction has to block until the data is sent. Okay, so here's what I mean by this. Say I got two tests, test 1, test 2. Test 1 is going to send 3 onto this channel. And test 2 is going to read whatever comes on the channel and put it into variable x, and you can see that there. So let's say task 1 hits its send first. It reaches send, it tries to send 3 on the channel. It will block, it will sit there until task 2 reaches its receive instruction. So 1 hour later, or however long later, task 1 will sit there for an hour or however long it takes until task 2 reaches that read instruction, the receiving instruction. And then once it does, then the data can be transmitted from task 1 to task 2, and task 1 can then continue. But task 1 doesn't want data to be lost in transit, because remember, this channel, it can't hold any data, right? So if task 1 were to continue and task 2 weren't there to receive the data, then the data would go away, right? And that can't happen. So task 1, if it reaches its sending instruction first, it has to block and wait for task 2 to receive. And I didn't show this example here, but same thing happens if task 2 hits its receive first, if the ordering was switched. So let's say task 2 hits the receive first. There's nothing to receive, right? It just blocks. Task 2 will block there until an hour later, say, task 2 finally sends 3 onto the channel. When that happens, then task 2 can continue. Okay, but either way, sending these two instructions, send and receive, they are blocking instructions. So if it's an unbuffered channel, the send will block until the receive happens, until the receive instruction happens in the other thread, and the receive will happen until the send instruction. The receive will block until the send instruction happens. So either way, and it has to do this because there's no buffering, or by default. We'll talk about that in a second. But by default, there's no buffering. So, you have to wait so that you don't lose the data. So note that when you use a channel in this way, the channel is allowing you to communicate, allowing you to send data between two different threads, two different Go routines, but it's also doing synchronization, right? Because task 1 has to wait for task 2 to receive, or task 2 has to wait for task 1 to send, right? So it is also doing synchronization. Just like the wait. Remember we talked about wait groups, right? I said, I want my main routine to wait for this Go routine to complete first, and I made this wait group, and so this is doing a similar thing. It's another way to do the same thing. Because task 2, it has to wait for task 1 to get to reach its send instruction before task 2's receive can continue, right? So there's also waiting going on here. So the communication with channels is also synchronous, and its synchronization is built in. So what that also means is that you can use this channel communication for just the synchronization and throw away the result, the received result. So here's the example I got here. Test 1, test 2. Test 1 sends the number 3 onto the channel. Okay. Test 2, notice that what it's got the arrow and then the C, which means to receive something from channel C, but it's not assigning it to any variables. It's not saying X equals arrow C. It just says arrow C. So in this case, task 2 is receiving something off the channel, but it's not using the data. It's basically throwing away the data that it receives. So in a situation like this, since you're wasting the data, all you're really doing is synchronizing the two tasks. So task 2 has to wait for task 1 to do the send. So this is like a wait with the wait group. This is like another way to implement a wait. Because task 2, even though it's throwing away the data that it receives, it still has to wait for task 1 to do the send. So you're waiting for an event just like you would do with a wait group. So it's something about the channel communication that is also synchronization built into the communication constructs. Thank you. Module 3, Threads in Go, topic 3.3, buffered channels. So the channels that we talked about so far are the default channels, and they have no capacity to hold data in transit. But channels can have some capacity. So channels can contain a limited number of objects in transit if you want. Now the default capacity for a channel is 0, so it's unbuffered. But you can make what are called buffered channels, which actually have some capacity to hold data in transit. So the capacity of a channel is the number of objects it can hold in transit. And the way you define this is an optional argument to the make function. When you create the channel, you can set its capacity. So in this example, I say c equals make chan int, comma 3. I give it that second argument 3, which tells me that the buffer is size 3. Now note that default size is 0. So default, when you don't give that second argument, is as if you made the second argument equal to 0 to say, look, I can't hold anything in transit. But in this case, I'm saying, okay, 3. I got a buffer size 3. Now, when you have a channel with a certain amount of capacity, the send and receive block under different conditions. Not really different, but it seems different. So what I mean is sending only blocks if the buffer is full. So what that means is, say I make a channel size of capacity 3. I can do 3 sends without blocking. So I can do 3 sends with no receipts. So say GoRoutine 1 is sending to GoRoutine 2. Let's say GoRoutine 2 has not done any receives. It doesn't do a receive for a long time. GoRoutine 1 can do 3 sends and still not block. Because what happens is when it does its first send, even though the receiver is not there to receive it, the buffer, since it has capacity 3, can hold it temporarily and allow the GoRoutine 1 to continue its execution. And this can happen up to 3 times, up to the capacity of the buffer, right? Now, eventually, once I get to that 4th send, if that receiver hasn't done receive, then if I couldn't write the 4th thing into the buffer. It only has capacity 3. So at that point, it blocks. Okay, so sending only blocks if the buffer is full, but you have some sending that you can do without actually having to block on the side of the writing go routine, which is good, right? Because blocking is generally a bad thing. For the most part, it's a bad thing because blocking reduces your concurrency, right? If you block, that means you can't execute, which means you might be wasting processor resources, right? So you don't generally want to block. You would like to be able to do a send, and then, whether or not the receiver is there, you just continue on your merry way and keep executing. So having a channel capacity allows that to happen to some extent. Now it's limited because memory is finite. The buffer can only have a finite size, but you can continue for more time without blocking, and so it can help you sometimes. Also, receiving, same thing happens on the receive end. Receiving only blocks if the buffer is empty. So if the buffer is full, it has 3 objects in it, you can do 3 receives without any sends because it can receive those 3 things that are in the buffer. Now on the 4th receive, once the buffer is actually empty, then that receive will have to block. Okay. So this is what it means to give a channel a capacity. You make it a buffered channel. You can give it a size, right? And the size means that the channel is basically storing data in transit, so the sender and receiver don't have to block as often, right? Because they can use the buffer as a holding space. So to give a little example, I got my channel with capacity 1. So I got two tasks, 2 threads, T1, T2, or 2 go routines. In between there is a channel, and it's just it's capacity 1, so it's 1 space, right? And you look at T1, it's doing the sending, T2 is doing the receiving. T1 is writing an integer in there, C, into the channel, and then T2 is going to read 2 things out of the channel. Now, first note that those, that can't happen, right? You can't send 1 thing and receive 2. So what happens exactly depends on which executes first, which send or receive executes first. But the first receive has to block until the send occurs. So if T2 is executing faster, it hits its first receive before T1 has issued the send, then T2 is going to block because the buffer is empty. Okay. But once the buffer gets filled, so once T1 executes and fills that buffer, then the first receive can continue. Now, the second receive in this scenario blocks forever. Now, I'm assuming that T1, it doesn't do any more writes, okay? So this would be an error. If T1 just writes one thing into the buffer and T2 tries to read two things, the second one has to block, right? So this would be an error right here. In fact, it would probably throw an error as soon as you run it. But so in this case, this is a problem. T1 is just going to block forever because it's waiting on T2 will block because it's waiting on T1. Now, we can see a similar thing happen in the other direction. This time, T1 is actually writing two things. 3 and 4 is writing into the channel. T2 is gonna receive. So the second send is gonna block until the receive is done. So the first send, the first send won't block. It'll just put something into the buffer, and eventually the receive will receive that out of the buffer. The second send, if the receive has happened, then the buffer is empty. So the second send can write something into the buffer and then continue. But if the receive has not happened, then the second send is going to block because the first send has filled up the buffer, and this buffer is only size 1. So the second send will have to block until the receive happens. So why use buffering? The main reason to use buffering is so the sender and the receiver don't need to operate at exactly the same speed. So what I mean by that is that if you don't have a buffer, if you use an unbuffered channel, then the sender and the receiver have to be in lockstep, meaning the send has to block until the receive happens. The receive blocks until the send happens. So they have to be in lockstep, which reduces the amount of concurrency that you can have. Buffering will allow you to do, like in this case, say you got an empty buffer, the producer, okay, so I'm defining this is like sort of a classic problem, producer-consumer. It's a concurrent example where you got two different threads. There's one that you refer to as a producer, one you refer to as a consumer. Now, the producer is basically generating data. We don't know how it's generating data. It could be generating maybe it's reading data from sensors, reading temperatures from sensors, and sending them to the consumer to be processed. Okay, something like that. But it's generating data on a regular basis. Like maybe, actually, a common thing is maybe it's doing maybe your T1 is connected to a microphone, and you're sampling the sound. So periodically, you have to record a sample, store a sample, and so the producer maybe is just talking to the microphone, grabbing samples periodically. And then it sends them to the consumer, and the consumer is doing some kind of audio processing task. It takes the samples and who knows, it does a fast Fourier transform, something like this. Okay, so but the general idea is you got a producer that is producing data from some source over and over and over again over a long period of time, and the consumer is consuming data over and over again over a long period of time and doing something with it. Now, a buffer is useful in this situation because let's say sometimes the producer is a little fast to produce its data, right? So it's maybe the consumer is consuming at a certain rate, but the producer is a little faster at producing. In that situation, the producer, if you had no buffer, the producer would have to block. If it tries to produce something before the consumer is ready to receive it, then the producer blocks, right? Until the consumer reaches its receive, and then they can continue. So the producer has to get slowed down to match the speed of the consumer, and vice versa. If you're consuming too fast, faster than the producer, then the consumer has to get blocked, its receive has to get blocked to slow down to the rate of the producer, right? So the rate, if these producer and consumer, one's a little faster than the other, their rate is forced to be slowed down when you don't have any buffer. Now, if you have a buffer, then a speed mismatch between, or at least a temporary speed mismatch between the producer and the consumer is acceptable. Because what'll happen is if the producer is a little bit too fast, then it'll just fill up the buffer. If the consumer is a little bit too fast, it'll just draw data from the buffer. Now since the buffer is finite size, this can't happen forever. Right? If the producer is forever too fast, then it will fill up the buffer and then it'll still have to block. But when you have a scenario where the producer and the consumer, on average, they're at the same speed, but sometimes they speed up and slow down. And this certainly happens in a lot of scenarios where they're not exactly lockstep. Sometimes the producer is a little faster, sometimes a little slower, and so on. Then a buffer is really helpful because then this buffer, as long as you don't fill up the buffer, can allow you to continue executing without blocking, continue sending and receiving without having to block because you got this buffer in between. But still, on average, the speeds have to match or else the buffer will overflow or become empty. Thank you. Module 4, synchronized communication. Topic 1.1, blocking on channels. So a common operation on a channel is to iterate through the channel. So iteratively read from the channel. So this would happen in a scenario where you had a producer and consumer. The consumer is receiving from a channel, and it just wants to continually receive data from the channel and then process it in some way. Very common scenario. Receive data, process, and you just continue as long as the code is running. So that's what this there's a construct made to do specifically that, this for range. So we've already seen for loops, but you can use this range keyword to continually just read from a channel. So for instance, here we say for I equal range C. What that'll do is it'll just iterate. That for loop will just continually iterate one pass for every piece of data that's received on that channel. So every time a piece of data is received on that channel, I is assigned to that data, and what's in the curly brackets is executed, right? The for loop is executed one pass, and it'll just continue forever. Or not forever, until a close happens. We'll talk about that in a second. But it'll just continually read data off of that channel and assign it to this variable I, or whatever variable you want to call it. Now in this case, and this toy example, I'm not doing anything useful with the data, I'm just printing it, but you could be doing anything in there, right? You just process the data and use it in some way. So this is a very common thing to do. Now, this for loop, it would be an infinite loop. It could be an infinite loop, right? So what has to happen is, in order to end this loop, when does it actually quit? It quits when you close the channel. So this is another method on a channel. You can close a channel. So you can see it. I have in the last line highlighted in red. The sender, the person who's doing the sending, it can call close on the channel. And if they call close on the channel, then the receiver realizes this close, and this for loop will end. Now, you don't have to ever call close on a channel. It's not like a file. You don't have to call close on a channel unless you're doing what I'm showing here. Unless you're using a range construct. If you use this range keyword to forever read from a channel, you need to close the channel. The sender needs to close the channel so that the receiver eventually knows, oh, I can quit this loop because now this channel is done. So the only time you would call close on a channel is if you knew, as a sender, you knew, oh, I'm never going to send more data on this channel again. Then you can call close, and that basically sends a message to the receiver to say, oh, now this channel is closed, so you can jump out of the loop whose range you're iterating through. So this is a sort of a very common thing to read from channels. Now, another thing that you might want to do is read from multiple Go routines. Okay, from multiple channels, really, which can be associated with multiple Go routines. They might actually be associated with the same Go routine, but reading from multiple channels, put it like that. So let's say, like in this example, I got these three Go routines: T1, T2, T3. T3 is receiving data from T1 and T2, and from T1 it's receiving it on channel 1, C1, and T2 is receiving on channel C2. So it's got these two channels. T3 has these two channels that it's receiving data from. Now, there are different scenarios about reading from multiple channels. Maybe, like in the case I'm showing here, maybe you need data on both channels. So you need, so for instance, it depends on totally it depends on the application, but let's say T3 is trying to compute the product of the two numbers returned from T1 and T2. Okay, so if that's the case, then you do what I'm doing here. Just read the two channels sequentially. A equals arrow C1, B equals arrow C2. So you read from both channels, and then once you get them both, then you print the product. Fine, it does the product. So in this case, we actually needed, T3 actually needed data from both C1 and C2. It needed both channels to complete its task, the product, right? And, these are blocking, right? These are blocking. So C1, so the first read will wait until something gets written onto C1, but then the second one, but eventually T2 will read from both of them and it'll do its task. But this is an example where you need data from multiple channels. But sometimes you have a choice. So sometimes you got a Go routine which can read from different channels, but it doesn't have to read from all of them. It just needs one of them, one or the other. So sort of there's an or relationship. You can get from this one or that one. You don't need all the channels. So if you have a choice, a situation like that where you have a choice of which data to use, and whichever data comes in first, that's the one you want to use, right? So say you got two channels, C1, C2, data could come in on C1, data could come in on C2. And in this scenario, whichever one comes in first come, first serve, that's the one I'm going to use and do something with. Okay. In that situation, you don't want to read from both channel 1 and channel 2, right? If you read from both of them, then you'll block on one of them. So say data gets sent on C1, so that read will work. But then the read on C2 will never happen because maybe data never gets sent on C2. Right? So you don't want to wait on C2 when no data is going to come, right? And vice versa. Maybe data comes in on C2, but not on C1, right? So you don't want to have to wait on both of them. In the last slide, we waited on both channels, C1 and C2, because we needed data from both channels, and we knew the data would come in on both channels. In this scenario, we just need data from one of the channels. And we don't know that data is going to come in on all channels. Data might just come in on one of the channels. And so we don't want to wait on all of them. We want to wait on just one of them, but we don't know which one. So that's the case where you use a select statement like I'm showing here. So select statement allows you to wait for the first data from a set of channels. So in this case, we got two cases actually. So in the select, you got the first case, the second case. First case is waiting on C1 to write it to A. Second case is waiting on C2. And whichever one of those two happens first, that's the one that's going to get executed. And so if the data comes in on C1 first, it'll do the first case and it'll skip the second case, and vice versa. Thank you. Module 4, synchronized communication, topic 1.2, select. So we've been talking about select, and I showed how select allows you to choose data from one of several channels. You don't have to block on all the channels. You can just block on the first one that comes in. The first one that's satisfied, where data comes in, then you can just wait for that, and you can continue your execution more quickly. Now, the way I described it before, the select was always, I was assuming that we were blocking on receiving data, but we can also block on sending data too. So with select, your case can either be receiving data from a channel or sending data on a channel. So I have that here. Let's say my first case, I say A is assigned to be arrow in-chan, right? So I have some input channel called in-chan, and if something comes in on that, then A gets assigned to that, and you print received A. Now the other case, instead of receiving, it's a sending thing. So in the other case, I'm taking some number B. I don't know what that is. I'm taking number B and I'm writing it to outchan. Now note that either one of these two cases can block, right? So like reading from inchan, that'll block if nobody's actually sent anything on inchan, and outchan, writing to outchan, will block if nobody's receiving on outchan. So either one of these two cases can block. And what happens with the select is, whether it's a read or it's a write, whichever one of the cases is unblocked first, that's the case that's executed. So if, in this case, if some data came in on inchan first before outchan became available, then you would execute the first case. Otherwise, if if somebody did some other Go routine did a read on outchan, then the second case would be executed first. So selects allow you to select either send or receive. You can block on either sends or receives and select one of them. Whichever one completes first, that's the one you execute. Now, a common use of a select is to have a separate abort channel. Okay, so say there's some task that you're doing over and over. You're reading data and processing it, right? So this is producer-consumer scenario again, right? Something is producing some data and sending it on a channel to you, the consumer. And your consumer, its job is basically to receive the data and then do something with it. So let's assume that the code I have here is for a consumer like that. Now notice that first thing, it's a for loop, an infinite for loop, right? It's an infinite for loop, because that's typical for a consumer. It's just going to keep receiving. Now then in there, I select, the first case is to receive data on the C channel and assign it to A, and then I process it. In this case, I just print A. And so I'll keep doing that. Receiving data, processing, until eventually there's an abort signal. So there's some other, somehow an abort happens, and that can happen any number of ways. Maybe another Go routine receives user input. The input user types in something that says quit. Who knows, right? So at some point after, normally what it wants to do is that first case, receive data, process the data. But at some point there's an abort that comes in on another channel. So you have this separate abort channel. And if anything comes in on the abort channel, then you just return, right? You just quit the whole process. Quit the whole loop. So this is normally an infinite for loop until that abort happens. So if some data comes in, and notice that we are not paying attention to the data that comes in on the abort channel. Notice that I'm not saying, it just says case arrow abort. I didn't say case X equals arrow abort. I just said case arrow abort. So I don't care what data is coming in on the abort channel. If something comes in on the abort channel, that means the user wants to abort, or somebody is ordering you to quit this loop, and then you just return at that point. So this is a common use of select. So you can have this separate channel that happens probably infrequently. So most of the time you're going through the first case, reading data and processing it off the normal channel, but every once in a while, at some point somebody's going to want to abort your procedure, and so you have a separate abort channel that you select from. Another thing that's done with selects is to have a default case. So this is a lot like a case, case switch in C, but or it looks like it. It's not the same, but it has a similar structure. You can have a default case. So in this case, we got the regular cases are waiting on channel 1, then the second one's waiting on channel 2. The default says, look, I don't want to wait on anything. Right? If neither one of those other if none of those other cases are satisfied, then I will execute the default. So I won't wait. I won't block at all. In this case, when I have a default, you don't block. You just go and execute the default if none of the previous cases are ready. Thank you. Module 4, Threads in Go, Topic 2.1, Mutual Exclusion. So we've been talking about channels, Go routines sending data back and forth through channels. Now, sharing variables between Go routines can cause problems. Okay, and I'll show you an example of this. But two Go routines writing to a shared variable, to the same shared variable, can interfere with each other. So one will try to write one number, the other will try to write the other number, and we'll get into an inconsistent state. And I'll give you a more concrete example of that in a few slides. A thread program is said to be concurrency safe if it can be executed, be invoked concurrently with other Go routines without interfering improperly with the other Go routines. So then you say, oh, this is concurrency safe because I know that when this runs, it won't mess with the variables of the other Go routines and alter them in some way that will ruin the other Go routines. So by this I mean, note that one Go routine can mess up the execution of another Go routine, right? So say this one Go routine is using a variable X, the other Go routine writes to that variable X while the first Go routine is using it. Maybe the second Go routine didn't intend for that variable to be written by this first Go routine, and so the first one Go routine can interfere with other Go routines. A Go routine function is said to be concurrency safe if you know that won't happen, that they won't interfere in these unsafe ways. So let me just give you some example of what do I mean by bad sharing. How can that happen? How can they interfere with each other? So let's be a little more concrete. Okay, here's an example of variable sharing going on. Okay, now all this is going to do is all it really does is it increments a variable I. Okay, so there's this variable I. We're going to start it off at 0, and I'm going to make two threads. In my main, I'm going to make two threads which just increment I, right? And each one is going to increment it once. So by the time they're done, I should equal 2. So I should start off at 0. You run these two threads to increment I, and then at the end, I should equal 2. So just to look at the structure of the code, there are two functions, the main and the inc function for increment. At the very top, I'm just declaring this global variable I. Also, I'm declaring my wait group. Remember, I make a wait group so that the main doesn't complete before the Go routines, before the sub-Go routines have a chance to execute. So I make the wait group. Now my increment function, all it does is I equals I plus 1, and then it calls WG done to know that you don't have to wait for it anymore. It is now done. Now then, my main function, I execute wg.add. I call the add method and I add 2 because I'm going to wait on 2 go routines, right? Because I'm going to have 2 go routines that I'm going to create that do incrementing, right? So I add 2. Then I invoke the 2 go routines. So go inc. Both of them should just increment this I. And then I do a wait, wg wait, waiting for both of these guys to finish. And then at the end, I just print I. So what I expect is that I should print 2, right? Because I starts off at 0. I initialize to 0 at the top. It should be 2 when it's done. But this doesn't always happen. So let's explain sort of why this doesn't happen. It happens because of all. It sometimes doesn't happen because of all the possible interleavings. Now, at first glance, it would seem like there's no real problem here because there are different interleavings, but the interleavings all look reasonable. They look like they don't cause a problem at a glance. So what I'm showing here is this table. There are 2 tables, 2 different interleavings. Each one of these tables has task 1 on the left, task 2 on the right, task 2 in the middle, and then on the right is the value of I. I just want to keep track of the value of I as we go through the code. Now notice I'm not showing all of task 1 and task 2. I'm not showing the done calls, okay? Because the ordering of the done calls doesn't really matter for this. But I'm showing that there are 2 different orderings for the I equals I plus 1. So in the top one, the top little chart, task 1 executes I equals I plus 1 first, then task 2 executes it second. In the bottom, task 1 executes second, task 2 executes first. But either one of those 2 orders, the value of I ends up correct. So if you look at the top ordering, look at I, right? It's 0 at first. After the first increment, it becomes 1. After the second increment, it becomes 2. And same thing on the bottom. Even though the task 2 does this increment first, it doesn't really matter because I is incremented twice still, so it goes from 0 to 1, 1 to 2. So it looks like either one of these interleavings is just fine, right? It shouldn't change the value of I. But that is deceiving. So really, there are a lot more interleavings than we're seeing here. The reason is because of the level at which this concurrency, this interleaving actually happens. So concurrency is at the machine code level, not the source code level. So what I mean by this is that the interleaving is not interleaving of Go instructions, Go source code instructions. What's actually getting interleaved are the underlying machine code instructions, right? So remember, the Go source code is compiled to machine code on whatever platform you're on. And so these machine instructions, which are sort of smaller instructions, those are what are actually getting interleaved. So what that means is for each one of these Go source code instructions, there can be like a sequence of machine code instructions that correspond to the Go source code instruction. And so the interleaving can basically partition, can interrupt right in the middle of a Go source code instruction. It can start interleaving right in the middle of it. So let's be more concrete. Let's take I equals I plus 1, the instruction that we're basically looking at right now. Now that might be, typically that would map to, that could map to 3 machine code instructions. First, a read I, where you read the value of I from memory, right? Because remember that most of these machines, they're register based. So you can't, when you do the increment operation, you can't just increment directly in memory. I mean, there are processes that do that, but most of the time, you first read the data from memory into a register. Then you do the arithmetic manipulation, and then you write the result back to memory. So those are the 3 steps I'm showing here. Read I, it goes to memory, to wherever the value of I is, brings it into some register. Then increment just takes the contents of that register as 1. Then write takes the contents of that register and writes it back to memory, wherever I is supposed to go. So that I equals I plus 1, it looks like one instruction, it's one Go instruction, but it's really a sequence of these 3 machine code instructions. Now, this is important to keep in mind because the interleaving actually happens at that level. So, and that's what gets confusing because, see, normally programmers aren't thinking about the machine code when they're writing their code. Or else if they were, then they'd be writing machine code directly, write assembly code straight. Now, generally, if you're writing Go code, you're thinking source code level, Go instructions. You're not thinking about the way that the Go instructions are subdivided into machine code instructions, not unless you are a hardcore coder. You usually don't think about that, right? So this is where people can get tripped up. So let's show the interleavings, the different possible interleavings again, except this time, instead of just looking at the 2 interleavings, task 1 does the increment first or it does it second, right? Those are the 2. Now we're going to take these 3 instructions, these 3 machine instructions, and interleave those and show how it can go wrong. Okay, so here's an example where it goes wrong. So this time you got task 1 left. Actually, I've the very left column, I've just numbered the line so I can refer to them. But you got task 1 and task 2, and then on the right you got the value of I. Now task 1, if you look at just the task 1's column, and first it's going to do a read in step 1. Then in step 3 it's going to do the increment. Then step 4 it does the write. And task 2, it has the same order. In step 2 it's going to do a read. Then step 6 it does an increment. Step 7 it does a write. Okay, so fine. The ordering is in each one of these tasks the ordering stays the same, but the relative interleaving can be different. And so notice the interleaving that we've picked, and I've highlighted the read instructions: read I, read I. Task 1 does a read I in step 1, and task 2 does a read I in step 2. So what happens is both of them have read the same value of I. So note that the value of I at the beginning is 0. So task 1 and task 2 have both read values 0 for I. Now then, task 1 goes ahead in step 3 and step 4, it increments that 0 to a 1, and then it writes it back to the location in memory where I goes. So it writes a 1 into the location of memory where I goes, and you can see that I is equal to 1. But remember that task 2, the read that it did in step 2, it still read a 0. So by the time task 2 does its increment in step 6, it's incrementing what it read was a 0, which was a 0, right? It's not incrementing the actual value of I in memory, which is now a 1, right? Remember, task 1 wrote a 1 back to memory in step 4. But that's not what was read by task 2. Because of this interleaving, task 2 read the old value of I, 0. So so task 2 in step 6, it increments that 0 to a 1, and then it writes a 1 in for I. Now, there was already a 1 in there for I. It writes another 1 in there for I. But at the end of this sequence, I has a value 1 instead of 2. Okay? So think about this for a little while. But the idea, the general problem is that when these two Go routines are sharing this I variable, right? They're both writing to it. The interleaving is happening at a finer granularity, at the machine code level, and that adds complications that people don't think about sometimes. Okay, so it's important to be aware of these. Thank you. Module 4, Threads in Go, Topic 2.2, mutex. So how do we do sharing of data correctly between Go routines? Don't let two Go routines write to a shared variable at the same time, just as a rule of thumb. Don't let that happen because you can get these interleavings that cause the problem that we just saw. So you need to restrict the possible interleavings of these Go routines. Say there are two Go routines, Go routine 1 and 2, which are both writing to this variable I, to the shared variable, shared data. Then you have to restrict their interleavings in such a way that you make sure that they can't both write to it at the same time. So access to the shared variables cannot be interleaved. You have to somehow, as a programmer, ensure that they can't both do that at the same time. So how do you do that? That is called mutual exclusion. You need to have code segments. You as a programmer have to declare code segments in these different Go routines which cannot execute concurrently, so that they cannot be interleaved. And so this action of, say, writing to shared variables. So say these two Go routines both write to I, right? I equals I plus 1, I equals I plus 1. You got to make sure that this Go routines segment where it writes to I is mutually exclusive with the writing to I for this other Go routine. So you have to declare these segments of code that are mutually exclusive with one another. And you have to do that as a programmer. So there are constructs, of course, built into GoLang to do that. So what we're going to use is in the sync package again, there's this mutex object. Mutex ensures mutual exclusion. Okay, there are several methods associated with mutex, but let me just describe it conceptually first. It uses what's generally called a binary semaphore. Okay, so semaphore is like the flag on your mailbox, right? If you have one of those outdoor mailboxes. So if the flag is up, that means the shared variable is in use, right? That means that somebody is using the shared variable. So like specifically, the shared variable, if we're trying to protect this variable I, right? There are two Go routines that are writing to I. Only one can do it at a time. So the flag should be up when one go routine is writing to I. And then the flag being down means the shared variable is available. So when this one go routine is done writing to I, then the flag goes back down. And then the other go routine knows, oh, now I see the flag is down. I can write to I if I want to. Okay? So each one of these go routines has to adhere to this protocol, meaning there's this semaphore, this flag, and it's binaries. These are up or down, 0, 1, right? If the flag is up, then you are not allowed to use the shared variable. Okay, because that means somebody else, some other go routine is using it. If the flag is down, then you are allowed to use the shared variable, but you have to put the flag up first. So you have to put the flag up and then use a shared variable. And when you're done using the shared variable, you have to put the flag back down so everybody else, all the other go routines, know they can use a shared variable. So there's this protocol that you have to, that the programmer has to write into their code and adhere to in order for this scheme to work. But this is the idea. Thank you. Module 4, Threads in Go, Topic 2.3, mutex methods. So we talked about these semaphores inside the mutex. You put the flag up, put the flag down to declare, put it up to declare you are using, a go routine is using the data, the shared data, it's writing to it, and then put the flag down when you're done writing to it. So these are implemented in a set of methods, lock and unlock. So lock, when you call lock, that basically puts the flag up, and when you call unlock, it puts the flag down. So you call lock, a go routine should call lock before it's about to use the shared data. And what will happen is if no one has the lock, meaning no go routines are using the shared data, then that first lock, that call to lock will proceed. It'll put the flag up, meaning set some binary value from 0 to 1 internally, and then it will continue, right? So it will not block. The code will execute in that mutually exclusive region, and it'll access the shared variable. Now, if while that's going on, say another go routine comes along and calls lock. Now remember, at this point, when the second go routine comes along and calls lock, the flag is already up, right? So when that happens, this lock will block. It won't allow the second go routine to continue and access the shared data. So it stops the second one. So whichever go routine gets into that region, calls lock first, it gets the lock. And the other guy, whoever the other one is, it has to wait. And notice that we're talking about 2 go routines. This could be any number of go routines. You can have 10 go routines all trying to share the same I variable, something like that. They all, like one of them gets in there first, calls lock first. Then there could be 9 other ones that try to call lock while the first one's in there, and all 9 will block. So that's basically what lock does. Now unlock is the matching thing. So unlock is the function that gets called when the go routine is actually done using the shared data, and it's effectively putting that flag down. So when this one go routine is done using the shared data, it's got to call unlock. If it doesn't, that's an error because it'll cause a deadlock. It calls unlock, and then what'll happen is one of the go routines that are waiting, that are blocked on their lock, will be able to continue, right? So if there were like 9 go routines that called lock and are now blocked, as soon as unlock is called, the first one that called lock that's in the waiting list, it will actually it'll be allowed to continue. It'll stop blocking. It'll be allowed to continue. It'll access the shared variable, and in this way, as long as you put a lock at the beginning, as long as every go routine calls lock at the beginning of its mutually exclusive region, and calls unlock at the end, then it ensures that that each one of these that only one of these go routines can be inside this region, this mutually exclusive region, which in our case is basically where the shared variable is being written to. So, so this mechanism is sort of generalizable to lots of different go routines, even though we're only talking about 2 right now. And here's a little example of it, how we would modify this incrementing problem. So this incrementing problem that we had, I'm fixing it now, right? I go to this increment function, and now I've done a couple of things. I've added, if you look at the second line, I've created a mutex, so called it MUT. And then the increment function, it still does I equals I plus 1, but before that it calls mut.lock, and after that it calls mut.unlock. So now that region in between the lock and the unlock, that is mutually exclusive with any other lock-unlock region. So remember with this example, these go routines, I had two go routines that would basically execute increment, and both of them have a lock and an unlock. Since they're both executing the same function, increment function, they both have a lock and an unlock before and after their regions. So those regions are exclusive. So only one of those two go routines can be executing I equals I plus 1 at a time, right? Because once one of them gets in there and calls lock, the other one is blocked on that lock until the first one finishes, calls unlock, then the second one can go through. So that's sort of a simple example of how you would do mutual exclusion. Thank you. Module 4, Threads in Go, topic 3.1, once synchronization. So we've been talking about Go routines, and we're going to talk about some of the features of the sync package. So sync packages gives you a set of methods that we can use to do synchronization between different Go routines. And here's another useful idiom that people perform a lot is initialization. So say you got some multi-threaded, i.e. multi-Go routine program running, and you need to perform some initialization task. Now, by definition, initialization is something that should happen only one time, and it has to happen before everything else happens, right? It should be the first thing, it's initial. So sometimes that's a little bit hard to guarantee when you have multi-threaded, when you have lots of Go routines that are running in parallel, because you don't know in exactly which order they're going to execute. So which Go routine should you have should you put the initialization in, right? Because you can't guarantee the order of execution of these multiple Go routines. So how do you do initialization, guaranteeing that there's some initialization function that happens one time, happens before everything else happens? How do you guarantee that when you have multiple Go routines? Well, one way is to actually perform initialization before starting the Go routine. So maybe you can do your initialization inside your main, inside the main, which would be the first Go routine. You could do it at the beginning and only then create the Go routines. But sometimes you may or may not have that option. So another facility that allows you to do this is part of the sync package is sync.once. So this once object, it has this method do, and one method do, and you pass it some function as an argument. So you can see there once.do f, whatever that function f is, and you can put this call to once.do, put it in lots of different Go routines. And this function f, though, will only be executed one time. So the Go runtime guarantees that even if this once.do is called in 20 different Go routines, only one of them will actually execute. And it also guarantees that all calls to once.do inside any Go routine, they block until the first one, the one that executes, actually returns. So that makes sure that the initialization executes first before anything else can proceed. So you can put this once.do at the beginning of all your Go routines, let's say. One of them will actually execute, and the other ones will block until it finishes executing. So this sync.once, it allows you, using once.do, it allows you to guarantee that first, initialization happens only one time, because only one of these once.dos is actually going to execute. Also, it ensures that initialization happens before everything else, because all the other once.do calls will block until the first one actually returns. So this sync.once is useful for when you need to do initialization and you have multiple Go routines executing. So let's show an example of where we might use that. So let's say we got two Go routines. And we're going to start two Go routines in addition to the main Go routine. We're going to start two Go routines, and we want them to do some initialization process, some initialization function, and do it only once. So each Go routine is going to be associated with this code do stuff. So if you look at the main right there, I have go do stuff twice, right? So I'm starting two different Go routines. Both are running do stuff, whatever that is, and I'll show that in the next slide. Also, just notice, we've done this before, but notice that I put the weight group. So I create a weight group at the top, and then I call wg add 2 to say I'm going to wait for two Go routines rather, and then I call wg wait at the end. This is to make sure that the main Go routine waits until these two sub Go routines actually complete. Otherwise, the main Go routine will just exit before the do stuff actually gets to do anything. So that's not the point of this, but I just want to mention that so you understand the code. All right, so we got these two Go routines that are going to do stuff, and they're both going to have to. One of them is going to have to do initialization, right? We need initialization done at the beginning of the stuff that's going to be done. So let's go to the next slide. So now first you can see on this slide a few things. First, at the top, we're defining our sync.once object, var on sync.once. On I called it. Call it whatever you want. Then I define this function called setup. So this function called setup is what I want to execute once. Think of this as my initialization. Now this could be whatever I want it to be. In this case, I just had it print init just to do something, okay? But you can have any sort of initialization operations in there that you want. So setup is a function that we want to have happen once. Now func do stuff down below is what's being executed by each one of the Go routines. So you can look at each Go routine, look at do stuff. The first thing it does is it calls on.do setup. Then it says print hello. So we should see hello printed twice on the screen at some point because there are two Go routines. And then it calls wg done just to let the wait group know that this Go routine is finished doing what it's doing. So now notice that both of these Go routines are executing the same code, do stuff. So both these Go routines have this on.do calling setup at the beginning of them, right? But what's going to happen is that only one of those is actually going to execute. Not both those Go routines are going to execute. Only one's going to execute. So when we execute the code, we get this appearing on the screen. You get a init first because that's the result of setup. Setup prints a init. So that's the initialization process, and notice that happens first, which is what we expected. Then hello, hello, you get twice because both of the Go routines do execute. Excuse me for the capitalization on one of the hellos, but both of them execute, and they both print hello. So this works. So init appears once, and init appears before hello. So the initialization is done before any of the other stuff in the Go routines actually executed, which is what we want of initialization. Thank you. Module 4, Threads in Go, Topic 3.2, Deadlock. So right now what we're going to talk about are problems that come with synchronization. So we've been talking about synchronization facilities provided in the sync package, also even outside the sync package with channels too. They also provide synchronization. But this synchronization, you can have problems with synchronization if you're not careful, specifically deadlock. So this is something you have to avoid when you're coding. You don't want to put basically build deadlock into your system. So deadlock deadlock comes from synchronization dependencies. So what I mean by that is you can have multiple Go routines, and synchronization can cause one Go routine's execution to depend on the other. Okay. So as an example here, we got G1, G2. These are two Go routines. And let's look at the top row. So I got in G1, there's a channel CH, and G1 is writing the number 1 onto the channel. Now on the other side, on G2 is reading from that channel. It's taking CH, reading something from it, assigning it to X. So there's a dependency here because G1 is writing onto the channel, and G2 is reading from the channel. So that's the dependency, and it's a blocking dependency in the sense that G1 it writes to the channel, but G2 can't continue past that line, that read line, until G1 does the write, right? Because G2 is going to wait, since it has to read from the channel, it's going to wait right there until G1 actually does the write. So there's dependency. G2 depends on G1. Its execution depends on G1. Also, there's data dependency here too. Data is being passed from G1 to G2 also, but we're less interested in that in terms of deadlock. But we're more worried about the execution dependency. G1's execution cannot continue until G1 executes its statement. And you can see the same thing on the bottom. In this time, instead of using channels, we're using mutexes. Okay, so say I've got a mutex object, and G1, it unlocks that mutex, and G2 locks it. So in this case, again, you can get a dependency because G2 can't accept the lock until G1 unlocks. G2 can't get the lock until G1 unlocks, right? So G2, again, its execution is dependent on G1. G2 can't continue past that lock until G1 gives up the lock. So in both cases, you get G2's execution depending on G1's execution. So G2 can't continue until G1 does something. So in one case, it's writing to a channel. The other case is it's unlocking a mutex, but either way. So synchronization causes these dependencies, these blocking dependencies. Now, when you can get into a problem, when you get into deadlock, is when the dependencies are circular. Okay, so what I mean by circular is if G1 is waiting for G2 and G2 is waiting for G1. Okay, so G1 is waiting for G2 to do something like unlock a mutex or something like that, and maybe G2 is waiting for G1 to write onto a channel. They're both waiting for each other to do something, but they're both blocked, right? So neither one of them can progress, and that's called deadlock. Nothing can happen at that point. So this can be caused by waiting on channels. It can also be caused by mutex, waiting on mutexes too, waiting for unlocking of mutex, but it can also be caused by waiting on channels too. So this type of circular dependency where G1 waits for G2 and G2 waits for G1, that's what you need to avoid in your code. So this is up to the programmer to avoid making such dependencies. So let's show an example of a dependency like that. So we're going to make a couple of Go routines in the main, and I'm not showing you the main right now. Right now I'm showing you do stuff. This is the code that each Go routine is going to execute. They're both going to execute the same code. This do stuff, it takes two channels, channel 1, C1, and C2. Two channels is input, and do stuff, first thing it does is it waits to receive something on the first channel, on C1, and then it writes a 1 on the second channel. So that's all it does. It waits to receive something on the first channel, and it writes to the second channel. And both of these Go routines are going to do the same thing. Now, they're going to have different arguments, as I'll show you in a second, but that's basically what they're going to do. Wait on the first channel, write to the second channel. Now, okay, so now in the main, here I'm going to, this is the main. I make two channels, CH1, CH2. They have integers. Then I have the wait groups, so we don't have to worry about that. But the main point is the Go do stuff. I got two calls to that, so I'm creating these two Go routines. Now, notice they both take two arguments, CH1, CH2. But the first call, the first Go routine, the first Go do stuff, it takes the order of the arguments is CH1 first, CH2 second. Then the second Go do stuff, the order's changed. CH2 first, CH1 second. So what this means is that, so remember do stuff that we just saw. What it does is it waits for to receive something on the first argument, on the first channel argument, and then it writes something to the second. So what that means is the first Go routine is going to wait to receive something on channel 1 and write something on channel 2 in that order. Now then the second Go routine is going to wait to receive something on channel 2, then write on channel 1. And notice how they're depending on each other, right? So the second Go routine is going to write onto channel 1, while the first one is waiting to receive something on channel 1. So the first one's going to be blocked. Then the second one is waiting to receive something on channel 2, where the first one is writing onto channel 2. So the second one is going to be blocked. Both Go routines are blocked, and nothing can progress. So this is an example of deadlock. So you have to avoid this as a programmer. Now, if you were to run that code that I just showed you, filled in with the details, if you run that code, GoLang runtime actually detects this deadlock. So if there's a situation where all Go routines are locked, which is what we just saw, right? All Go routines are stopped. Then the GoLang runtime automatically detects it, and you get an error like what I'm showing here. These are just the first few lines of the error, but basically it gets an error, says there's a deadlock, and it lets you know, which is a good thing. However, the GoLang runtime cannot detect when only a subset of Go routines are deadlocked. So when that happens, then it'll lock those. They'll be deadlocked, and you won't know it in any obvious way. It's just your program won't operate correctly, and you'll notice it somewhere down the line. It's harder to debug. So this type of deadlock, these type of circular dependencies, have to be avoided by the programmer. Thank you. Module 4, Threads in Go, Topic 3.3, Dining Philosophers. So now we're going to talk about the Dining Philosophers problem. This is one of these classic concurrency problems that people use to talk about synchronization and show basically possibility of deadlock problems in synchronization. So this is one of the classics. I mean, you always teach this when you talk about concurrency. So we're going to talk about it and sort of show how deadlock can sneak up on you. You have to be careful to avoid it. Okay, so in this problem, you got 5 philosophers sitting at a round table. Each one has a plate in front of them, a plate of rice, okay? And they're chopsticks that they're going to use to eat this rice. So one chopstick is placed between each adjacent pair of philosophers. So there are 5 philosophers in a circle. There are also 5 chopsticks between them. Now, everybody wants to eat their rice from the plate, but you need 2 chopsticks to eat the rice. So every philosopher, in order to eat, is going to have to pick up a chopstick on the left, pick up the chopstick on the right, and then eat. Okay, but only one philosopher can hold a chopstick at a time, right? So when one philosopher is eating, his neighbors can't eat, right? Because he's got both of the chopsticks, so the neighbors don't have their neighboring chopsticks, so at least one of them, so they can't eat. So there are not enough chopsticks for everyone to eat at once, and this is key, right? So, not that necessarily one can eat at a time. You can have multiple people eating at a time, but you can't just, they can't all eat at a time, right? So they have to be properly ordered in order to all eat. So the problem with this is if you implement this in a naive way, or I wouldn't even call it naive, but in a way without thinking it through, you can easily cause a possibility of deadlock in the system. So yeah, here's a picture of our table. Got this round table. There's 5 plates for the 5 philosophers. And then you see those little sticks. Between those are the chopsticks. So there's 5 chopsticks. And so in our model, when we code this, we're going to make each chopstick a mutex, right? And that makes sense because a chopstick can only be held, taken, or locked by one philosopher, right? So a philosopher, so there's a chopstick, the one at the top, right? There's a philosopher to the left of it, philosopher to the right. Only one of them can grab that chopstick at a time. So they can only have mutual exclusive access, so it makes sense to represent a chopstick as a mutex. So a chopstick is a mutex, and then each philosopher is going to be associated with a go routine, because it's going to be eating. Its go routine is going to be the action of eating. But it's also associated with 2 chopsticks, one on the left, one on the right. So every philosopher is going to have a left chopstick and a right chopstick. So let's look at how we might code this in an obvious way. First, we'll define our chop S as chopstick, our type, and that's just a sync mutex, sync.mutex. So that's a mutex, like we were saying. Then we make our philosopher type, and that's a struct with 2 things: a left CS, left chopstick, and a right CS, right chopstick, and those are both pointers to chopsticks. So we got our philosopher, we got a chopstick. Now, the philosopher is going to have associated with it a method for eating. So this is what we're gonna say the eating method looks like. So it's an infinite loop. See that 4 at the top, and what it does is it basically, the philosopher, first thing it does is it locks the left chopstick, then it locks the right chopstick. So then it's got both chopsticks. Locking is basically picking up the chopsticks off the table. Then it eats. So format, I just print eating to represent the act of eating. So it eats. Then when it's done, it puts down the chopstick, puts down the right chopstick, puts down the left chopstick. And by the way, the order in putting down chopsticks doesn't really matter for us. So that's what eating is, and it's an infinite loop. It's just going to eat over and over and over. And each one of these 5 philosophers is basically executing the same code. So now in the main, I'm omitting some of these details, weights and such, but the main, I'm just getting to the heart of it. First thing, if we look at this code, we're initializing. We're doing some initialization in the main. First initialization, first few lines are creating the chopsticks, and the next few lines are creating the philosophers. So we got to make 5 chopsticks and 5 philosophers. So if you look at the top, we make this slice for 5 chopsticks pointers, and then in that loop from I equals 0 to less than 5, we create these chopsticks and fill in this array. Okay, so we create these new chopsticks, 5 of them, all numbered C sticks 0 through 4. Then we do the same thing with the philosophers. So we make this philosopher slice right there, enough for 5. Then we have another for loop. And we create the philosophers. We fill in the philosopher array. Now notice, philos I equals ampersand, because these are pointers. And then the constructor, basically when I construct it, when I call philo, I'm passing it 2 things, okay? Now remember the order, the order of the structure field. So philosopher is a structure, right? It's got left chopstick, right chopstick. That's the order, right? So in the curly brackets there after philo, you can see 2 things. The first thing is going to be the left chopstick. The second is going to be the right chopstick. So the first thing, the left chopstick, is C sticks I, right? So if this is philosopher 0, the left chopstick is going to be chopstick 0. And then notice that the right chopstick is I plus 1, modulo 5, right? Now you have to do the modulo 5 to account for the last philosopher, philosopher 4. So what this means is that philosopher 0 is going to have chopstick 0 as its left chopstick, chopstick 1 as its right. Philosopher 2 is going to have chopstick 2 as its left chopstick, chopstick 3 as its right. But philosopher 4, he has chopstick 4 as his left chopstick and chopstick 0 as his right chopstick. It's in a circle, okay? That's why you have to do the modulo 5, because there's no chopstick 5. He gets chopstick 0. So we had to do I plus 1 modulo 5 in there, but basically you get the idea. So we've created in this in here, we've initialized the set of chopsticks, 5 of them. Then we made 5 philosophers and associated their left and right chopsticks with each one of the philosophers. Now, this program, so this is basically, this is almost it. One more thing we have to do in the main after we do this initialization is we have to actually create the go routines, a go routine for every philosopher, and get him eating, right? So we have, right after that, we start the eating. We say for, I have a for loop, I equals 0 to 5, because we want to make 5 go routines, 1 for each philosopher. We just say philosopher I dot eat, and it calls this eat, which is an infinite execution. So this will start each philosopher eating, and so starting these 5 go routines. Now this we would also, I'm not putting this in here, but we'd also have to add the weighting, the weight group, some weighting in the main, some form of weight in the main, so that the main doesn't complete before these philosophers complete. Because the philosophers, the way I've written it, these philosopher go routines will never complete. They're in an infinite loop, right? And so we got to make sure that the main doesn't complete either. So we would have to put in a little synchronization in there, a weight or something like that. But I just want to focus on the philosophers for the moment. Okay, so this is sort of how you would write the code in a naive way. So the place where deadlock can happen is if all philosophers, if they all grab their left chopsticks at the same time. Now remember, if you remember their code, so this is a little summary of the code that each one of the eat code for a philosopher. First it grabs its left chopstick, locks its left, then it locks the right, then it eats, then it unlocks the 2 chopsticks. So now we don't know what interleaving is going to happen with these between these different philosophers, right? But there is an interleaving where each one of these 5 philosophers, it executes its first lock, locking the left chopstick, and then and without going on, right? And then the next philosopher does that, grabs its left. The next one grabs its left. Each one of these 5 could grab its left chopstick before they continue. And in that state, if they all grab their left chopstick, meaning they lock the left chopstick, then all 5 chopsticks are locked. Okay. So then, when they try to execute their next instruction, locking the right chopstick, they won't be able to, because all the chopsticks are locked. Because your right chopstick is somebody else's left chopstick. So if everybody's locked all the left chopsticks, they're all locked, and we would be in a deadlock situation. So there's an interleaving here, at least one interleaving, where you can get into this deadlock situation. And it's easy not to see that. It would be easy to code this the way I just coded it and run into that type of deadlock. Now, this is a sort of a fundamental problem. There are lots of solutions that have been proposed, ways to fix this. One way to fix this, so Dijkstra's way, in this particular case, Dijkstra's a genius. Anyway, Dijkstra, he decided to fix it by basically modifying the code, and I won't show you the modification really, but he wants to modify the code so that each philosopher picks the lowest numbered chopstick first. Okay. Now, here's what I'm showing there in the blue is the code that we have. Okay, and our code does not do that. Our code, the first one that you pick up is the one to your left, which is the lowest, which is for most of the philosophers, that's the lowest numbered, right? So if you're talking about philosopher 0, to his left is chopstick 0, to his right is chopstick 1. So the lowest numbered chopstick is chopstick 0, right? So, and that's the one that he picks up first, the left one. And so that's true for all of them except for philosopher 4. Philosopher 4 on his left, he has chopstick 4. On his right, he has chopstick 0. And he picks up, 4 picks up chopstick 0 first. Picks up 4 would, according to our code, 4 would pick up chopstick 4 first, and then pick up chopstick 0. Okay, so the code that we have violates this rule that I have in red, picking up the lowest numbered chopstick first. If you change the ordering, so it always picks up the lowest chopstick first, then philosopher 4 would pick up chopstick 0 before chopstick 4. And it would try to pick it up, and if they were about to be in a deadlock situation, if everybody else had picked up their left chopstick, then philosopher 4 would be blocked, because it would try to pick up chopstick 0, but it would already have been picked up by philosopher 0, right? So then you wouldn't get into the blocking, you wouldn't get into the absolute deadlock state that we would have. Then it wouldn't pick up his chopstick, since it tried to pick up chopstick 0 first, it would never get to picking up chopstick 4, which means that philosopher 4 would block, and philosopher 3 would be allowed to eat, because philosopher 3 could then grab its right chopstick 4, and it could eat, and then we could continue, okay? So there's no deadlock in this situation, but philosopher 4 may starve. So what that means is that philosopher 4 in this setup gets lowest priority, right? He's the one who ends up having to wait on others most of the time. Okay. Now, so that's called starvation. He would, I mean, it's literal starvation in this example, but that can happen in other scenarios too, where you have multiple threads, multiple Go routines. They're all executing, but some number of them don't get to execute as often as the other ones because of the way you've made because of the way you set up your synchronization. So starvation is another issue, but deadlock is the worst, and you can avoid it in several ways. But just be careful of these circular dependencies. So this is a case where you have a circular dependency, but the circle is 5 philosophers long, right? The dependency, it has to go through all 5 philosophers before the circular dependency completes itself. So it's a little more subtle to see. Thank you.